Refineries. Improving refinery economics is very important to sustain in this business. See, any refinery mantra is basically improving the GRM, gross refining margins. Gross refining margin is just fundamentally value of products leaving the refinery minus cost of the crude entering into the refinery. And to achieve that, we'll have to do the reducing of the fuel and loss, of course, selection of right crude oil at optimum cost, and then now the molecular management is the next thing which we need to get into, because the molecular management can happen in the downstream units, secondary units in the refinery. So we'll have to see, we manage each and every molecule, the right molecule in the right place to get the right product, which is marketable and then which gives money to the right crude refinery. And because of the changing demands, product demands, there is a flexibility to switch in the product is also very much important. How best we'll be able to blend the different streams and then make the products available into the market. Because of the fluctuating demand, so this flexibility in refinery to switch from one fuel to the other, though it is limited depending on the configuration, but within the configuration, how best we will be able to do it, that is the trick of the operating refinery. Of course, the controlling giveaway of the specifications, so there are BA specifications are there. So normally refineries focus very much on to be on dot on the specification so that the economics can work out. And capacity utilization, these are all the mantras for all the refinery operators, because refinery operations is also part of the topic. So I just covered under refinery economics, each refiner where all they will focus. Optimizing the operating cost, reliability in operations, of course, lowering the inventories, and most important is and then unplanned shutdown controlling. And turnaround time reduction, see on dot whatever the planning is happening, so within that time we should be able to come back. And of course, the energy is the most part of the refinery operating cost. So operating refinery in energy efficient manner, of course, personal efficiency index, and finally leveraging onto the digitalization techniques. See, in any refinery, the crude oil cost and the blended stocks itself will cover almost 85% of the total cost. And the rest 15% is only covering the all these bullet points what we have covered. Like maybe fuel and loss or fuel and fuel gas, it will contribute around 6% of the overall cost. And power will be around approximately 1%. So maintenance and then operations will cover around 3.5 to 4%. And rest is the cat to make a refinery economically viable. Because 85% of the cost is crude cost, because of the other situations, regional and then geopolitical situations, that cost is sometimes beyond our control as far as the Indian context. And improved economics. Digitalization techniques will be useful. And then it is the mantra for every refinery as of now. See, every refinery is going towards the digitalization path. So in the digitalization, basically, we have to process more data than crude. See, the crude processing is one side, but there is enormous data that will be generating in the refinery. So the data need to be brought at one platform, analyze the data, and based on which the decisions can be taken. So with that, the refinery can be operated in a more efficient manner. See, AI and ML are such techniques where these data gathering can be done at one place. And of course, in the refinery, technology-wise, a lot of technology has come. IoT devices are there, which will make the equipment to speak. See, instead of we doing many things, the equipment itself will give a lot of feedback. And embrace emerging technologies to ensure safety, reliability, and optimization. So the equipment itself will prompt its need for maintenance, and then the digital twins are there available. So digital twins are also being implemented in the refinery. And to manage all these digitalization techniques, of course, the skilled workforce and tools and technologies are also very much required. So basically, the focus themes for the digital refinery, if you see, in the safety wise, reliability wise, operational efficiency wise, project management, integrated supply chain, and then employee productivity. If you see in HSCC front, most of these techniques are already being implemented by different refineries at different stages. So the real-time location sensing is one important in case of health, safety, and environmental issues. Robotics technology is picking up like anything in the maintenance and inspections, like drones inspections are there, and then of course the tube cleaning, boiler tubes cleaning, heater tubes cleaning with robotics, and then tank bottoms cleaning with robotics. So a lot of technologies are being implemented across refineries. Of course, when the technology is coming up, then the cyber security platforms also need to be robust, and carbon footprint measurements, and then video analytics are also playing a very important role, like perimeter intrusion detection systems, etc., in case of security. Asset reliability management, of course, asset integrity management systems are also in place in refineries, wherein the predictive analytics based asset monitoring maintenance, post 3D models, digital twins. In case of operational efficiencies, as we discussed earlier, energy optimization, real-time energy optimizers are in place, warehouse managements, digital walls, all these things, handheld electric devices, smart glasses for log field readings. Most of these techniques are already being implemented to improve the operational efficiencies. Because when it comes to the project management, end-to-end management solutions are there, digital solutions are available, those are being implemented. And more so the turnaround management, because it is in a specific time period, it has to be completed. A lot of digital techniques are being used to manage the turnaround within the time and then bring back the refinery or petrochemical back into operations. The other supply chain management related digitalization techniques are also being implemented, vendor management, of course, procurement management, etc. Employee productivity also, HR analytics tools, AR/VR based technical trainings, internal collaboration, robotic process automations, all these things are also being implemented in almost all the refineries and then petrochemical complexes. So now these are all some of the thoughts on the downstream operations and then the technologies, different technologies, and with respect to the digitalization. I think this is what I just want to briefly touch upon each of these topics. And I thank CSIR-IIP for giving this opportunity. If any questions are there, it's most welcome.
Thank you very much, sir, for your very thought-provoking presentation. And this presentation was full of learning, and which can be used to improve the downstream processing and whole industry. And thank you very much.
Thank you.
Now, we will take the questions and answer at the last of the session. There is a Q&A session. And now we move to our second keynote address, which is basically on comprehensive pathways to achieve net zero goal. And it will be delivered by Dr. Ajit K. So, welcome, sir. And Dr. Ajit K. Das is currently head of refining R&D Center in Reliance Jamnagar Refinery. He joined Reliance in 2006 and established the Refinery R&D Center at Jamnagar. Prior to that work, he worked at Indian Oil R&D Center since 1985. He is PhD in chemical engineering with R&D experience over 35 years. And he has developed and commercialized many technologies. For example, INMAX, MCC, DSO, EPR, etc. He has more than 100 patents and more than 80 publications with 7 book chapters to his credit. He has received many awards and recognitions He was the president of engineering science in the last Indian Science Congress in January 2020 at Bangalore. Now I request Dr. Nasid Kedas to kindly deliver the lecture.
Yeah, thank you. Thank you, Dr. Kumar. Thanks to Dr. Manoj and also to IIP for inviting me to share some of my thoughts. Let me go to the presentation first. Can you see my? Okay. So as the slide suggests, I'm going to talk on a very contemporary topic, that is competitive pathways to achieve net zero goal. No. Net zero is a very holistic topic, but it is also a compulsion topic, because without that, the whole planet won't survive. So let's see that how we can run refinery and petrochemicals, but still run it in a sustainable manner. This is a disclaimer slide. Basically, what it means is that whatever I am going to talk and present here, it is on my personal capacity, and Reliance has no responsibility on that. I'm sure you all know Reliance. Reliance is a mega scale operation, and it runs projects in a very, very large scale unit operations. But it has two of the world's largest refinery integrated petrochemical units. But what is important also is that it has multiple business areas, digital and Reliance Retail also is there. And the recent one is that our Honorable Chairman has declared 4 gigafactories, all on renewable and new energy. That is solar PV, battery energy, fuel cell, and green hydrogen. So all through electrolyzer. So these factories are getting established in Jamnagar area. You will hear a lot more about that. Let me come to the main topic of today. That is, how do we achieve net zero? What all things are required to be done? This is a summary slide. I want you to draw your attention on this scope. So when we talk of net zero, we have to remember there are basically 3 scope protocols are there: scope 1, scope 2, and scope 3. Scope 1 involves the direct emissions within the refinery or in the plant premises, direct emissions of greenhouse gas. And the greenhouse gas typically are mainly CO2, but there are many other SF6, methane, N2O, and hexafluorocarbons, NF3. All these are greenhouse gas. They have different impact factors. But coming back to defining the scope 1 is direct emissions. Scope 2 is indirect emissions from purchased energy, like purchase of electricity, heat, or steam. If we are importing from outside other plants or other premises not belonging to the refinery, then that comes under scope 2. And scope 3 are basically other indirect emissions, like if we are selling product like gasoline, diesel, etc., and customers in when they are running vehicle, that will also lead to greenhouse gas emissions. So in scope 3, all those indirect emissions also are to be included, including the business trips and all renting of buses, waste management. So there are all other indirect emissions included in scope 3. We all know that in just 200 years from 1800 to 2001, the net taking the base, the global warming effect is 1.2 degree in 2021. And by 2100, if we do nothing, if no measures is taken, we'll be reaching a kind of 3-degree increase in the planet temperature, which is going to be having a devastating effect. And in the bottom part of the slide, the impact of the different greenhouse gases is shown that CO2, although is very important because it is bulk, but the role of methane, nitrous oxide, and HCFC are also not to be neglected because their impact factor is much higher. Let me talk about few important terms in the sustainability. We talk about carbon neutrality. What it means is that it covers scope 1 and scope 2 needs to be net zero balance. But when we talk of net zero emission, it also includes scope 3. So if a company says that we want to be net zero by 2035, that is what Reliance has declared, that we want to be net zero by 2035. What it means is scope 1, 2, and 3, all the emissions need to be net zero. Carbon offset, you are hearing, going to hear, that is compensating CO2 emission within own boundary by funding low or no CO2 emission technology elsewhere. So that is what we call offset. You will also hear term on carbon credit. One carbon credit is 1 ton CO2 emission reduction. You can buy or sell carbon credit. It's valid today in EU and US, but it's getting into our country as well. There are renewable incentives which are being offered by Government of India, typically in terms of capex and some other savings and tax benefits. There is also renewable energy certificate, REC. One REC is 1 megawatt hour of renewable energy. One can buy or sell REC in India. And typically the REC costs about rupees 2,000, that is rupees 2 per unit, which is almost like a solar cost, solar power cost rupees 2 per unit typically. There are other terminologies like renewable identification number, which are attached to the biofuel in order to tag and get certain incentives. This is there in US and EU. We may also have to get into this trend if we want to really incentivize the biofuel in a big way. Mass balance certificate. This is a new term coming. This is done to ascertain how much is the biogenicity and circularity within a refinery and petrochemical setup, how much biofuel is getting processed, how much of plastic circularity is established. To do that, there are certain certification agencies who can provide this kind of mass balance certifications. Now, circularity of plastic. Today, any plastic, if you can process it back, it is circular. Whether you make fuel or you make chemical or you make plastic, it doesn't matter. But this definition is being countered, and very soon, if you make fuel from plastic, it may not be considered as really circular. So one has to look how to convert a waste plastic into virgin plastic. That is really the sustainable plastic circularity. That definition is being adopted now in EU and US, and probably that is what is the most sustainable way to make plastic circular is converting waste plastic to virgin plastic. We all know green chemistry. There are 12 principles of that, but atom economy is one of the most important principles in that. Let me come. This is a summary of how do we achieve carbon neutrality or net zero. There are 3 ways. One has to minimize CO2 generation, then maximize using carbon neutral feed, and third is fixing carbon as materials or as or store it. So in regards to minimizing CO2 generation, we talk about improving energy efficiency. We adopt renewable energy, and also we can store energy and produce green hydrogen in night time and use it in night. So there are ways to minimize CO2 generation in the plant setup. Maximizing carbon neutral feed, like using biomass, which are renewable feedstocks, because biomass, while the agro crops are getting produced, they are actually capturing CO2 through photosynthesis. That is how the atmospheric CO2 comes down when you have a lot of trees and agriculture. So we have to make sure that the agriculture is also sustainable in terms of water and in terms of it should not consume fuel like that. It has to be renewable also. So feedstock like biomass, MSW, organic, agro-based waste biomass, these are all carbon neutral feed. As regards fixing of carbon, we can make chemicals, we can make materials, we can also utilize for varieties other applications of CO2, and we can also sequester CO2. Now let me tell you, whatever limited study we have done, these pathways have their own benefits and own drawbacks. For example, chemical fixation to chemicals, cost of mitigation will be low because these chemicals are they have good price. So economics of projects would sustain on its own. So there is no CO2 mitigation cost per se, but the volume involved is less unless you talk of very big change, like we have a multi-zone cat cracking for oil to chemicals, like crude oil to chemicals. It can convert the entire crude oil into chemicals, thereby it can fix the carbon as chemical. Bitumen is another example how you can fix the oil in bitumen and it will not produce CO2. So, but these are all having limited volume applications. Biomass per se is again a low cost because it is available at a cheaper price and amount of CO2 mitigated is high. So this is a very good option. You see, both are green here. Biomass, low cost and high volume, you can adopt that. So that's why this has got certain potential. CCUS, it has high mitigation cost because the initial capex requirement is high. But at the same time, you can mitigate a large amount of CO2. And as regards renewable power, again, the capex cost is high and its amount of CO2 mitigation potential is very high. So these are some of the typical characteristics that how things work out. Now let me take you, I'll try to give some example of how one can manage to achieve net zero, what it means really. What it means really is that we have to make net zero CO2 where the CO2 mitigation cost is minimum, but at the same time capex is minimum, margin is maximum, risk is minimum, and whatever existing refinery asset we have, that has to be again fully utilized to the extent possible. And at the same time, we have to also look that the natural source like land, water, etc. are also optimally utilized. And what it really means that it is a big scale, mega scale optimization problem. And in that you have to bother about how do you produce power, how do you produce steam, how do you make fuel for the refinery, where heaters, etc., has to be managed, furnace heaters and all that. How do you produce hydrogen, store hydrogen production and storage, and then efficiency improvement and making chemicals, CCS, carbon offsets. So these are all different portfolios on which one has to look into overall mega scale optimization so that at minimum capex and opex, one can achieve this net zero. This really calls a system engineering approach for net zero, wherein what is system engineering? We talk about this is an art and science of finding optimal solutions for very complex systems, which is system of system, like multiple plants put together, even multiple refinery assets and refinery petrochemical assets put together, along with utilities, need to be optimized in a global scale with varieties of feed supply, product value, risk mitigation, decision analysis, and multivariable optimization, wherein scope 1, scope 2, scope 3 of all the scopes, CO2 emission need to be managed. So it's a mega scale system engineering simulation and optimization. That is what is the point it is leading to. I am not going into details, but each of these portfolios like biomass, renewable energy, hydrogen, each one has some specific characteristics, advantages and disadvantages. You know, the slides are all there. You can have a look to it. But typically, I would say in summary in this slide is that the biomass is going to be an important portfolio because next 20, 30 years, till the battery storage, etc., in the renewable are picking up fully in an economic manner, biomass is going to play a very decisive role. In 2050 onwards, we see renewable energy will actually take over almost 60-70% of the net zero. The new energy would be coming through renewable. So this is where the future is. But currently the transition, biomass is going to play a very big role because already waste agro biomass is available. If we can make use of them, it would be very good. Hydrogen is a carrier, energy carrier. It can be a very good source, but again, lot of cost issues are there. It has to be brought down cost-wise. One important element is the CCS. You know, now US government has come up with $70 to $90 a ton of tax reduction in incentive in terms of CCS. One of the major hurdle in CO2 capture and sequestration is really capture. One can develop many technologies, but the sequestration is the real bottleneck today. It involves a lot of cost and there's a very big risk involved. There's a risk of CO2 coming out from the storage space unless it is stored properly. There's a large scale capex involved. So this is a very risky area, but it is a very important area to take up because without this large scale CO2 solution would be possible. Renewable energy is one area and CCS. These are two major areas where the future of CO2 mitigation volume-wise will be quite good. So in India, we need to take care of this. This is again a summary. Since the time is very short, I thought I prepared slide for half an hour, but I now see 20 minutes. How much time do I have? Hello?
I think it may take 2, 3, around 5.
Summarize. See, in the solar PV area, right now polycrystalline is the main thing, but in future monocrystalline is going to take over in a big way because of important cost-wise it is somewhat higher today, but efficiency is much better because that is where the future is. And also this IBC, SGH and BF, this is where the envisaged PV would be there. You know, the silicon heterojunction with both sides and monocrystalline, bifacial and monocrystalline. This is the area where really things are shaping up. This is a summary of how the battery space is looking at and what are the costs of the renewable energy in different form. I'm very happy to tell you that the solar PV in daytime is actually cheaper than coal and LNG today. You know what this table shows that the base is solar PV, which is now about 2.3 rupees per unit. One can get solar PV in daytime. That's the price of power. And if you want to produce the same thing, it will cost you 2 rupees more in coal. Just grey coal, with all CO2 emissions. And LNG is also costly now. So, and if you look at if you add battery storage, this includes lithium phosphate battery, solar PV plus lithium battery. It would add to your cost 4.9 rupees, just our additional storage. So if you want to do, it will cost you 4.9 rupees more per unit. Here it is base is say 2.3. So additional 4.9 rupees, just for 9-hour additional storage if you want to do. What it means is that the battery cost today is quite high. It has to come down in a very big way in order to make the renewable power be able to give round the clock basis. Today, solar is economic, much cheaper than even fossil, but it is only for daytime. If you want to cover renewable energy for 24-hour basis, the battery cost has to come down almost like 70 to 80%. Then it would be beating the fossil, the gray fossil. Of course, the cost for blue fossil, the cost again would be more. You can see this also gives an idea between gray and blue. The energy cost would be additional $3 extra would be coming up. Just to give you an idea what it really means. Thermal energy, if you want to make steam, for example, thermal energy can be a very big storage space through CSP. Like concentrated solar can be, it converts the thermal part of the energy and stores the thermal energy through either molten salt or through air and sand. This technology is very good if your objective is to make steam, for example, because here direct product is steam. So this is a very good storage. Now, as regards steam, you can see again the cost, different varieties of energy source. If your target is to produce steam like syngas, gray, you don't do any CCS. This is the baseline here. It's about, let's say, $15 a ton. Now, you look at CSP-based steam, this is on round-the-clock basis, you will be able to make it at minus $4. So it will beat your syngas gray. But the capex here is on higher side. So if you are ready, and this can last quite long. So what I'm trying to say is some of the renewable green source of energies are even cheaper today, but their capex should be higher. So that is where it is today. Biofuel, for example, if you want to produce steam from biofuel, from agrobiomass, you will be able to get at the same price as you are making syngas. From pet coke, if you make syngas and produce steam, that cost and the steam produced from biofuel today would be almost same. If you produce bio-CNG through anaerobic digestion, it would cost you another maybe $5 per ton. It would be slightly higher side. But depends on, like, if you want to convert, e-fuel, and if you want to use e-fuel, which can be produced CO2 plus hydrogen, that cost today is much, much higher. So you have to, what I'm trying to tell you is that these portfolios are so competitive in some sense that one has to do a very, very quick, very good optimization overall basis to find out where is the real solution. Hydrogen can be a very, very important carrier as well as a source for supplying energy, and a lot is being done to produce green hydrogen. As you know, a target of $1 a kilo is set, and that's a very steep target. If we want to achieve that kind of target, there's an enormous opportunity here. At the same time, it's a challenge. I'm happy to tell you that Reliance has developed, and we are putting up a demonstration plant of 50 tons per day. This is based on our new catalytic biomass gasification technology, which converts all the agrobiomass, solid agrobiomass, into hydrogen. This is the rough sketch technology. It's a breakthrough in terms of science also, because we are engaging a supported solid catalyst, which actually does a solid-solid catalytic reaction, because feed is a solid, like coal, pet coke, or even biomass. These are solid feed. And we are engaging here a solid-solid catalytic reaction in the gasification, which accomplishes this conversion from biomass to hydrogen in single step almost in entirety. We get at about 700 degrees centigrade, we get full conversion of all these feedstocks. And we produce about 11-12% net of hydrogen yield is there, weight percent. So this, as I said, it has zero tar in a way, because it gives very good conversion in terms of catalyst. We are putting up a first time demo plant of 50 ton per day. Biofuel is again a very, very important area. We need to make SAF, synthetic jet fuel, there are varieties of feedstocks available, like agro residue is there, gasification, biomass gasification. We can use vegetable oil, used cooking oil. We can import palm oil, and we can also do hydrothermal liquefaction of municipal solid waste. Now, in all this, you can see the cost of SAF. This table shows the cost of SAF production. And the baseline is the jet price at $60 crude price. If you look at it, the cost of production of SAF is very different in different parts. You see, hydrothermal liquefaction of MSW is one of the cheapest way to make SAF. The other cheap way is if you make thermal pyrolysis or catalytic pyrolysis and then convert through hydrotreating. But let me tell you, some of these technologies are still passing through a lot of development stages, because hydrotreatment of these biofuels is indeed a big challenge. So there are many, many options available, and that is what probably is the trigger for doing a lot of R&D in these areas. This is again an area of very large importance. How do you reduce cost of CO2 capture? And I'm happy to tell you that we have developed a technology which actually brings down the capex and opex of CO2 capture by 70%. So you can see different compared to standard amine process. Now, hindered amine process which reduces by 30% the OPEX. So we have a solid adsorbent based technology which minimizes the energy consumption in a very big way. We are also planning to have demonstration of this technology. As I said, the cost of sequestration, capex cost and the risk involved is quite high. Some of the options like bitumen, needle coke, enhanced oil recovery, it does not cost for mitigating and storing CO2, but the volume involved is limited. If we want to plant trees, it costs about $5 per ton of CO2. Through tree root, nature-based solution, if you want to have, the mitigation cost per ton of CO2 is $5, which is very good. If you have $70 CO2 mitigation cost being offered by government, you can easily plant trees and get going, provided you have a lot of land available. But saline aquifers and basalt, these are all, particularly saline aquifers, have certain risks involved. Basalt is a low reactivity, and some of the rocks have this kind of properties to capture and store CO2 in a big way. So these are areas, emerging areas, where a lot of research needs to be done in order to make the technology risk-free. This is a summary slide. Our chairman has already declared a lot of investment is being made on these areas, and our target is to achieve the new energy goals through gigafactories for battery and green hydrogen, fuel cell, electrolyzers. These are all areas, and a lot of activities are on. And as you know, Reliance net zero target is 2035, and we are very actively pursuing this goal. One important thing is the supply chain and the mindset both need to be changed significantly. We talk about the old economy is oil and gas, catalyst, chemicals, LNG and steel. These are the current scope of refinery and petchem. The future scopes are all electrolyzer, biomass, green steel, green methanol, battery, advanced materials. So these are new keywords emerging. And today's target in refinery, minimizing cost, quantity, emerging markets, quality, and time. These are typically where refinery, petchem, and other manufacturing units spend their time today. But in future, also it has started. The environment issues like CO2, carbon footprint, offset quality, alternative energy, circularity, biogenicity. These are new keywords emerging. And the driving force is the social change in terms of health, safety, human rights, anti-child labor, gender equality, healthy lives, So these are the new pillars of sustainability are actually going to work hand in hand. That is how the whole process of manufacturing will become sustainable in future. Yeah, thank you. Thank you. I took little time. Sorry for that because I had certain slides assembled. Uh,
Thank you very much, sir, for the in-depth presentation on various important aspects leading to the carbon neutrality. The presentation was full of learnings, and I believe that this learning can be helpful to academia as well as industry to contribute to the nation's goal to attain the net zero targets. And really thank you. Now we will move to our next invited lecture, and that lecture will be delivered by Dr. Ravi Kumar from Biofuel. And Dr. Ravi Kumar is a chemical engineer working as the Chief General Manager R&D at Corporate R&D Center, Bharat Petroleum Corporation Limited, India. He started his career with Engineers India Limited in 1990 and worked for 11 years before joining BPCL. He has over 22 years of research experience. He holds a BTech degree in chemical engineering from Andhra University, Visakhapatnam, and Tech degree in chemical engineering from Indian Institute of Technology, Kanpur, and PhD from Imperial College, London. He won prestigious Commonwealth Fellowship in 1995 for pursuing his PhD at Imperial College, London. He has published over 50 papers in reputed international journals and conferences and contributed to several patent applications. He authored a chapter on fluid catalytic cracking in the Handbook of Petroleum and Natural Gas Refining and Processing, ASTM Manual Series 2030. His area of research interest are refinery process, coal gas to liquid technologies, syngas to methanol and DME, modeling, simulation, scale-up, and optimization. He has received Outstanding Aluminous Award in Engineering by AU College of Engineering in 2013. Also, he received awards for innovation and indigenously developed technology from Petrofed, Green Tech, MOPNG, and Frost and Sullivan. Now I request Dr. Ravi Kumar sir to kindly deliver his lecture, please.
Thank you for the introduction. I hope I am audible.
Yes,
Hello?
it's a loud.
So you are able to hear me, sir? Hello? Yeah.
Yes, sir.
You are able to hear me?
Yes, sir. Yes.
Yeah. Thanks for the introduction and thanks for inviting me for the talk. So the topic of my presentation is BP Mark, a real-time crude assaying for monitoring and optimization of crude distillation units. This is basically a patented technology developed by Bharat Petroleum Corporate R&D Center. And the outline of my presentation is as follows. What are the challenges with the conventional laboratory methods of crude assay? And why BP mark is needed, and what is the methodology behind this particular?
Excuse me, sir. Sir, your presentations are not.
Pardon me?
Presentation slides.
Yeah, presentation you are able to see or no?
No, sir.
Already. Oh, okay. No, already shared this. It's in share mode only. You are able to see?
Yes, sir.
Oh, okay, thank you. Okay. This is a brief outline of my presentation. That is what are the challenges associated with the conventional laboratory techniques and how the BP mark is different from this particular process, and in terms of methodology and what are they basically, what kind of reports it can generate and where we have validated, and also some trials and where all we have implemented. And finally, I'll close by sharing with you how the development of digital twin model along with AspenTech softwares. And they have created an icon for integrating this particular tool in AspenTech suite. Basically, distillation evaluation basically involves two steps. One is atmospheric distillation and another is vacuum distillation following ASTM standard protocols. Both these tests involves a detailed experimentation, and it takes a lot of time, and individual cuts you will be separating using the normal distillation process under atmospheric and vacuum conditions, and then you will test for each cut basically the yields, and also test for properties for each cut, and generate almost 200 to 300 data points. Whereas the difference between BP mark and conventional method is it doesn't require all the elaborate procedure. It only requires 4 bulk properties. One is API or density of this particular crude, sulfur content, kinematic viscosity, and micro conversion carbon content. Once you give these parameters, so through established nice correlations and models, it can generate the TBP curve, crude characteristics, and distillation residue characteristics. What will be the hydrogen consumption typically when you subject to vacuum gas oil to hydrocracker operation, or FCC DCU yields and bitumen information, and it can also generate the fuel oil recipe. So therefore, it is going to be very useful for oil suppliers, international trade, supply chain optimization, advanced planning, and real-time optimization at unit level, and also as a refinery as a whole. So this particular software, as I told you, it's fully integrated with the AspenTech products, and it can be used for real-time monitoring and optimization because it gives within 2-3 minutes the entire crude assay, and which can be used for all your digital models. And the one advantage is the models are basically very, very accurate, and these correlations are developed based on a large database. And even if you use a single particular crude, because in refinery of contamination, because of the contamination in crude tank level, etc., it will be the properties will change significantly. The advantage of using this particular tool is you will always up to date with respect to crude profiling. So on a bulk, it gives key characteristics. What is the gas, LPG, naphtha, kerosene, gas oil, and vacuum residue profiles, and also the gas composition. And the beauty of this particular product is all this information comes in the Excel format, and around 500 data points are generated within less than 2 minutes. And even cut-wise information is also available. Like for example, naphtha in 6 cuts, kerosene 4 cuts, gas oil 5 cuts, vacuum gas oil 6 cuts, and LR and vacuum residue, long residue and vacuum residue. And this particular tool has been validated at 5 different laboratories in India. And also we have subjected this particular tool for different API crudes. Like for example, API starting from 9.6 to 56.23. And in all cases, the predictions are pretty accurate. And we approached the ASTM committee also for including this as a new standard, and this is under active consideration. So we also use this particular tool for real-time monitoring and optimization of crude distillation units of CDU video, which I will be sharing some details in this brief presentation. So as far as real-time monitoring and optimization is concerned, what we all need to do is basically you have to draw samples from the tanks that are coming directly from the pump house, and then feed that information to BP Mark for generating the assay. And this particular information, it goes to technology setup and all. Then they can use it for real-time monitoring and optimization of this. And first you have to wait for 4 to 8 hours because this plant has to reach some kind of a steady state, and then you can estimate what is the differential value addition with respect to by changing the yields, etc. Typically the value additions are in the range of 0.1 to $0.5 per barrel. So before going into the details, I will tell you briefly about the validation part. And this particular software has been validated for several days in all 3 shifts by taking all 3 shift average. As you can see, this red line is the BP Mark prediction, whereas the green line is the plant data. And if you use database information, for example, today I'm running with Bombay High or Mumbai High, Middle East crude. This is the profile what you will see, and whereas with the BP Mark, those 4 properties, the predictions are very close. Similar exercise we carried out for Kochi Refinery. Here the differences are because the in Kochi Refinery they are using different swing cuts. So we established that the swing cuts whatever they are using are not accurate, and as a result of that small differences are noted, and this can be closed very easily. That's what we did, and subsequently this particular software has been validated with several other trials. And this tool also has been validated at IOCL Panipat data, using IOCL Panipat data, and also HCAM database, and also other refineries. So I'll explain you in Kochi Refinery case real-time optimization. So once we have this tool, and as I showed previously, you can have the real-time assay and put into a digital tool and close the gap. This is how we have closed the gap, and this is the recent data. As you can see, the predictions and the actual plant performance are very close to each other. Okay, so based on the economic analysis, this chart shows what is the BP Mark suggestion and how the plant is operating. In majority of the cases, they are going hand in hand, and the economic analysis of distillation profile and price of each product based on that we have calculated, and they are closely matching with each other. So I'll briefly touch upon the AspenTech digital twin model. This is only the previously whatever I showed you, it's only based on simple cut point adjustments. To reap more benefits, what you can do is you can use the digital twin model by taking the real-time crude assay and generating the TBP analysis, and this particular assay information we can put into it. As I told you before, this particular thing, AspenTech has created a ribbon for accessing BP Mark icon, and through BP Mark you can generate the crude assay, and this crude assay can be sent to real-time optimization tools like Aspen-1 and PIMS software for offline optimization and refinery-wide optimization. So this is the stepwise procedure. As you once you click in this Aspen HYSYS, you will get the access to this tool, and you have to basically give the laboratory information to the BP Mark, and you can integrate with the Aspen digital twin model, and based on the real-time optimize data, this Aspen-1 plant data that can be fed. Once you have the crude assay and the plant information, you can simulate the results and correct your set points and inform the DCS panel that the cut points have to be changed. because in the earlier slides, I've shown you the offline optimization is not going to give you the complete picture. Whereas once you have the online digital detailed model with you, you can do many more things. So offline optimization through basically at a cut point level will help you to some extent. But once you have online tool with a detailed digital tool, then it is going to help you in more closer optimization. Similarly, this particular tool can be used for refinery-wide optimization. The reason is, see, for example, in FCC, the crude properties, the feed properties will change continuously, or if you are having different crudes and things like that, and depending on the tank, what you are processing. So if you have the ready-made information with respect to feed properties, you can take online decisions whether to process more residue or divert some part of atmospheric residue into FCC column and etc. Similarly, hydrocracker pre-feed can be optimized based on the hydrogen consumption rates. The software also gives you the delayed coker yields. So based on the distillation potential, etc., you can decide how much vacuum gas oil to be shifted, or how much residue has to be processed in a delayed coker unit, etc. So similarly, the catalytic reforming unit, based on the naphtha properties, you can have a fair idea about hydrogen production potential and accordingly optimize the hydrogen plant, and isomerization based on the stream properties and the requirement of gasoline and overall plant optimization. So coming back to the digital twin for real-time optimization, the potential benefits are mainly in terms of energy saving and also maximizing the value-added products and reducing quality giveaways that you have seen in the previous slides. Once if you take only swing cuts, there will be a lot of gap between reality and the actual operation, and because of that you lose a lot of money, and as a result of that you lose a lot of money. So this tool will help you in achieving maximum possible potential, and at the same time it reduces the laboratory role, and virtual online, it can work as a virtual online analyzer also. So in summary, so we refiners often process mix of crudes for which accurate SI is not available on real-time basis. Because of that, our decision making is highly challenging. So therefore, if BFmark can be used in those kind of situations, and because it is generates the entire crude assay within no time, and this particular accurate data you can use for characterizing the product streams, and any unknown crude mix also it can be analyzed very quickly, and it is ideally placed to fill the gap that exists in the crude oil blend evaluation and provide accurate predictions within an hour to facilitate the decision making process. And this more importantly, it is integrated with daily uses tools like Aspen PIMS and Aspen suite of products, and this can be used for online optimization also. It is going to give a lot of benefit, around $0.3 to $0.5 per barrel. So with this, I close my presentation. Thank you, IIP, for giving me the opportunity, and thank you for your patient listening. Thanks a lot.
Thank you very much, sir, for giving this very detailed presentation of the BFmark. And it seems a very fantastic tool to handle the current scenario of processing many different tools in the refinery, which have different variation in with respect to yield, and to basically integrating the actual simulation tool, and which can be really very helpful, not only to increase the gross margin of the refinery, but to overall optimization of different processes. And thank you very much, sir. And now we proceed to the next invited lectures that by Dr. Pramod Kumar, and title is Crude Oil to Chemicals, Dr. Pramod Kumar is a Deputy General Manager in Corporate R&D Center of Hindustan Petroleum Corporation Limited, Bangalore. He has more than 21 years of experience in process design, research, engineering, and technical services in the area of FCC, thermal cracking, biomass pyrolysis, carbon nanotube, crude to chemical. He holds an MTech degree in chemical engineering from IIT Kanpur. He is responsible for commercialization of FCC feed nozzle, catalytic disc braking processes, high olefin FCC catalyst. He holds more than 15 patents in various areas of research. Now I request Dr. Pramod Kumar to kindly deliver his lecture.
Hello. Thank you, sir. And first of all, I thank the CSIR-IIP for giving me an opportunity to talk about the crude to chemicals. And I'll be talking mostly about crude to chemicals and what HPCL is doing in this area. So, as has been talked in the keynote speech, like crude to chemical is the way forward. So, it's set the tone. So just to give a brief about HPCL R&D Center, probably many of you may not be knowing. So we are located at eastern part of the Bangalore, almost like 43 kilometers of the airport and 30 kilometers from the city center. So we started our journey in 2012, in the top one can see, where the temp level set up. And then we moved to the entire campus in 2016. And then the phase 2 of our campus has been set up in 2022. So we are pretty new in the area of energy research and development. So far we have set up 16 labs in the two phases. There is the phase 1, we have the labs starting from the crude, chemical synthesis, FCC, hydroprocess, process modeling, simulation, catalysis, bioprocess, standard testing, nanotechnologies, we are here into the polymers, fuels, battery, engine, corrosion, thermal separation, residue oxidation. So this is just a brief about HPCL R&D Center. So coming to the top of my presentation about the crude to chemicals, the content is like this. So as had been talked in the keynote speech, for the refining industry, there are various challenges starting from strain on the margin because of the crude price volatility, environmental impact. There is a sulfur demand like has to be coming down. The other challenge is with respect to the environmental impact because the CO2 emission is quite high. Then there is an advent of electrical vehicles. So that is putting up another challenge to the refining industry. Then again there is an entry of renewables like biofuels. We are talking so much about the green hydrogen. So these are all positive challenges to the refining industry. Then there is a futuristic transport like hyperloops and all. So all these things, if you see, it is creating a lot of pressure to the refining industry. Now, where is the way forward in such scenarios to the refining industry? If we see this graph, basically, the gasoline demand is reduced, diesel demand is marginally increased, but the demand of the LPG naphtha is continuously increasing. This indirectly shows that the petrochemical feed demand is growing, and so far the data gives like 70% of the oil demand going forward is going into the petrochemical sector. This again, this data shows about the 5-year cycle. If you see the blue colors, it shows even in the pandemic or in the 5-year cycles, the demand of the fuels are going ups and down, but the petrochemical feed demand is continuously on and it is going up. Similarly, the next graph shows about the LPG intake and the naphtha demand, which is continuously increasing. So all this shows like there is a demand of the feedstock for the crackers. So this is again a old data, but what it conveys is that compared to the GDP, the demand of the olefins and aromatics is higher. Similarly, if we see that this is all because there is a rising demand, a rising GDP, rising middle class, then there is an unprecedented growth in the Asia Pacific, and the petrochemical growth is more than the GDP. That's what we talk about. So this slide, this was talked in the keynote speech when the petrochemical demand or the consumption in the country is very low, 9.7 compared to the world average of 30. So if we see the gap and the demand of the petrochemicals in the country is almost like 56 MMBPA is the demand, and gap is almost like 27 MMBPA. So almost like every 18 months, one cracker of very big size has to be put up in the country to meet the demand. So that much demand is there in the petrochemical. So what we are seeing, there is a challenge in the industry and there is a demand on the petrochemical. So the way how the refineries has to move towards the petrochemical. So what are the ways we see in the subsequent slides? So this data only shows about what are the tractors coming up in the world and in the country. So now we come towards the refinery petrochemical integration and crude to oil chemicals. So this is a simple refinery where the petrochemical yield will be less than 5% and almost like 95% will be the fuels. So if the mid-gas and the propylene are added, so it will go to that 15%. Again, if we add paraxylene and all, it can go to 20%. Again, if the crackers are added, it can go based up to 30%. That's what we are seeing in the latest crackers coming in the country. But going forward, if you directly convert the crude to the chemicals, it is told like it can reach up to the 80%. So the fuels, 90% going towards the petrochemicals, almost 80. So it's almost like a 180-degree swing between the fuel to the chemicals. That's what we are talking that stage. So this is just shows about the history, like how it is moving. So the first is the simple recovery of the aromatics were in 15%. This was 390, then 15 to 20% by forward integration of the crackers. Then the third stage is about the scale and the portfolio complexity, like deep scale conversions of the paraxylene and the olefins, which we see in the subsequent slides. And then the 2020 onwards, we are all talking about crude to chemicals, which is more than 40% of the chemical feedstock. So now we'll see worldwide in the under situations how the refiners or the petrochemicals are moving. So there are three-pronged approach. The first is, we know like FCC is the key makers of the propylene and the glutenes in the refinery. So the way out is the refiners, if you see now, moving towards the high, like the high severity FCC units, and they recycle all like naphtha, sulfurous, which are the precursors of the propylene. So the propylene can go like 20%. And we are there in the like HPCL, we have our own technology which will discuss about this. Second is about the integration, like you have the refinery. So the way forward is to put up the crackers or the other petrochemical units so that one combination could be the higher quality FCC and followed by the crackers. Next could be the bottom upgradation units could be put up which can feed to the crackers. So we are having like in our HRRS, this configuration is coming up refinery in the petrochemicals. Then the third is about the crude to chemicals. Now, we talked about crude to chemicals, but what are the ways to reach the crude to chemicals? One is the steam cracking, which was put up by ExxonMobil in 2014, wherein it was a thermal cracking. Next is the catalytic cracking, is another route. Third is the combination of the hydrocracking and the steam cracking. Now, coming to the first point, which we talked about the FCC, high olefin FCC. So there, just want to say, it's an R&D center. We developed the technology. We call it HP squared. That means Hindustan Petroleum High Propane FCC technology. This basically is built on the platform. We know like a FCC platform, but the differentiation is it has a unique hardware. I think that means it's a multiple rising configuration, and the catalyst is in-house developed catalyst by HPCL. We have got 2 patents on this, on the hardware as well as the catalyst. And in the lab scale, lab and the pilot also, we have this 50 kg per hour per day pilot plant wherein we demonstrated more than 20% propane we can achieve with this catalyst and the hardware. So we are planning to go for the scale up of this technology. Now, since we talk this technology has 2 components, hardware and the catalyst. catalyst is very easy to implement in the like in the HCC unit. So far we have been almost like more than 700 tons of liquid catalyst. This catalyst per se can be used as an additive or co-catalyst in the conventional HCC unit, which operate at a low severity. And we are using this catalyst in all our 4 HCC units at Mumbai Refinery and Vizag Refinery. The advantage of this catalyst in the conventional HCC units which we have in our refineries, it increases propane, it reduces the bottoms and it increases the ROM. This catalyst cannot be used in our HCC unit because the severity is limited and we don't have the downstream gas plant to capture or to separate so much olefins. Further, after trial in our HCC units, we have demonstrated this catalyst successfully in one of the high olefin HCC units in the country, where we supplied 400 tons of this catalyst and we got 1% higher propane than the incumbent catalyst which used in the refinery. And this catalyst per se is a very low net by end catalyst, so it makes it a very, very low cost condition to the refiners. Now we'll talk about crude to chemical. So as we said, crude to chemical is a concept where the chemical yield will be more than 40%. So broadly, there are 2 routes. One could be the hydrocracking and HCC, followed by the acidic cracking. Now there are two ways to convert crude to chemical. One is like we have the well-established technology available in the refineries that can be deeply integrated. So there is one way is well-established multiple units. So we have to bring the synergy and get maximum chemicals that's possible. Another concept is a single unit concept, which is the keynote we have seen. Dr. A.K. Das talked about the LCC technology of the Reliance. We also have discussed about it. So this summary is a little cluster of many information, but directionally, if we see that traditional integration is the crude oil we have. So in the refinery, people will put steam crackers and get the ethane and the propane. Second, we talked about the direct crude cracking, wherein the crude can be taken as a light crude. It can be steam cracked and it can get propylene, ethylene, and the butane. Second is the COTC complex, that's the crude oil chemical complex, wherein crude oil can be again put up into the steam crackers and then butane, ethylene, and propylene can be made. Now there are 2 announcements recently made by the Aramco Lamas CNG, and the second is on with the technique. One is called the TC2C, second is the CC. One is the thermal one, second is the technical cracking based on the FCC platforms. There the talk is like it can produce more than 70% of the petrochemical units. But both the platforms are built on combinations of the available technology in the refinery and the petrochemicals. So this figure shows about like in China, so many petrochemical like CSIR-IIP complex are coming out. So the intent or the key takeaway of this slide is, if you see the capacity of the COTC, it is almost like the refineries. But right now, whatever the petrochemicals in the country we are all talking about 1.5 maximum 2 MMTPA carriers. But if you see the COTC complex are comparable like a refinery configuration, 20 MMTPA configurations, and the investment also you see it is similar to the refinery configurations. And if you see the second last column, the petrochemical yields are almost like hovering from 40 to 60% in the China. So these units, couple of them already. So we'll talk about one of them. One is the Henry configuration. So if you see this Henry configuration, it's all having the well-established new build units. Then there is the emulated bed configurations, and there are 3 reformers. So it makes almost like 4.5 MMTPA of paraxylene from the 20 MMTPA. So it is more of a paraxylene configuration, but in this configuration there is no steam crackers. So it's all around the refinery units combined into different things and making the almost like 42% of the petrochemicals. Second configuration, I'm just talking about, it is about the heavy crudes. If you take 5 MMTPA of the crude, so almost like 3.5 MMTPA chemicals can be produced. This is again based on different slurry hydrocracking configuration, but there are numbers of the steam crackers which can be used to make the chemicals. Basically, whatever the critical bed reactors are there, they are making a precursors of the steam to the crackers. So next, we'll talk about like in this crude to chemical what HPCL R&D center is doing. So this is a typical slide wherein crude is taken to the sequence between there are a number of the available units, and if you see the naphtha crackers typically used in the refining petrochemical configuration, and that produce the petrochemical unit. So we have seen there are a number of units to produce the petrochemicals, and by refinery and the petrochemical configuration so far we are able to reach almost let us say 30% of the petrochemical needs. So what in HPCL R&D proposing a technology we call HP code. Code means it's like a crude oil to olefin and aromatic technology. So we developed this technology and demonstrated in the pilot scale. We have got 3 patents on this technology. We have done the FTO for this technology as well. So what we are talking is crude will be directly taken to the HP code, which will produce the petrochemical feedstock. So it will broadly have 2 units only, and it will produce more than 40% of the petrochemical within the single unit. And so far in the lab scale, we have already reached 48% of the petrochemicals, and we are striving to reach around 60%. So in this technology, we are not taking any external source of the feed. It's the only the crude is being taken, and we have the multiple reagent configuration. It's a single unit direct conversion of the crude. It uses the fluidized bed reactor configuration. It's a combination of dense phase and the dilute phase configuration. The catalyst is in-house developed by HPCL. And it is very easy to integrate the existing refineries. And of course, it's a less capital incentives be intensive because there is no crackers into this. There is no pre-treatment of the food. Feed energy is very, very less. It's flexible operation. If you want to go to different mode, if you want to increase the fuel also, it's very much doable. It requires no footprint because there is no many units are used in this.
We are basically considering the time constraint.
Yeah, just 2 minutes, I mean, 2 minutes. So far we have completed the pilot system, technology and is completed and will be done. I just want to announce our board has approved to put up a 80 KTA plant. So we are going towards that right now. So summary of the presentation, in the current situation, there is a need to convert crude to chemicals, either integration or standalone. And if we see the current configuration, there is not a single solution. It will differ from the naphtha based or the diesel centric. So COTC configuration is based on the crude quality, depending on the evidence of the feed, the configuration can vary. Single state COCTC is a possible solution. And future COCTC, it bio-based source or the plastic recycles can act as an additional feedstock for this. So with this, I come to the conclusion of my presentation. Thank you for hearing. Just one announcement on behalf of HPCL. We are conducting one event called the New Generation Idea Contest 2022, wherein it is open for all the researchers, including the undergraduates also. So there are 10 themes on this, and the last date for application is 15 September. So and there is also an award for the institute which is submitting more applications for this. Thank you.
Yeah, thank you very much, sir. Thank you for delivering this detailed presentation on pathways, technologies, and configuration to achieve the basically goal to maximize the petrochemicals from food processing. And thank you, sir. And now we move to our next invited lecture that will be delivered by Mr. Krishna Mani. Krishna Mani currently holds the position of Senior Research and Development Manager in the hydroprocessing, renewable energy, and gas processing development group in Honeywell Indian Technology Center, Honeywell UOP Gurgaon. He has about 19 years of experience in refinery operations, process engineering design, and research and development. He graduated in chemical engineering from University Department of Chemical Technology, UDCG Mumbai, and has completed a postgraduate program in business analytics from Great Lake Institute of Management, Gurgaon. He holds 16 patents in clean, sustainable fuel and chemical technology development. Now I request to kindly proceed for the presentation.
Thank you. So first of all, we'd like to thank the organization of CSIR-IIP for inviting this talk. It's a great honor to present our technology portfolio. Sorry. Also, I'd like to thank the Technical Management for giving this opportunity to physically come here and give this talk to this audience. So today I will be covering an interesting topic on sustainable fuels and how kind of transition from refined linear engine for producing clean fuels towards the unit which also produce petrochemicals. But in future, we are kind of moving towards a phase where this will not only produce clean fuels, but petrochemicals, but also sustainable. So how this transition is going to happen, and how one of our technologies is helping that transition covering in details. But before covering, since I'm representing a company, so based on the Security Exchange Act, there will be some statements which are forward-looking statements, which basically mean that there are some projections which are based on some assumptions and they may or may not pan out. So from an investment perspective, we need to keep that in mind. So with that, I will give a brief introduction about Honeywell. So Honeywell is a established headquartered company and product portfolio company operating in different states of aerospace, building technologies, performance materials, technology solutions, and then saving productivity solutions. So these are the four verticals. I am basically part of the PED division, which takes care of technology development for refinery area. The brief about Honeywell India. So Honeywell India has a presence of about 6 hubs in India, primarily operating from Bangalore, Pune, and Gurgaon. We have about close to 8,000 scientists and engineers working across this span of various portfolios, supporting technology development both for global as well as for the local needs. I am basically representing the R&D center, which is located in Gurgaon, basically focusing on sustainability solutions, petrochemical, and sustainable energy development. So, just to give you a brief, Honeywell pledged for the carbon neutrality last year. So this pledge basically talks about being carbon neutral in its operations by end of 2025. And this is primarily with respect to scope 1 and scope 2 emissions. There is a commitment to scope 3 as well. The last several decades, we have invested close to 5,000 sustainability projects, which helps in resource optimization and then also participating in cleaner and sustainable development. In this particular theme, I will be covering an overview of the separate business division called Sustainable Technologies. We'll also talk about what are the macro drivers which are driving this particular area. We'll talk in depth about Profile, which is a technology which helps in producing green fuels. We'll also look at another offering called processing, wherein it's the lowest cost of compliance to produce green fuels in the existing refining assets. And then we'll have a little bit overview about what are the new emerging areas which are coming in terms of green. So sustainability technology solutions, as you can see, is a broad portfolio under PNP, and it covers 5 different areas or 5 subcategories. One is renewable fuels, we'll cover in detail. The second one is about plastic circularity. A lot of waste plastics are getting generated. How we can create a infinite loop for a circular economy of using the same plastic, producing recycled polymer oil, doing distinct patterns, or basically producing again recycled plastics. So kind of creating an infinite loop. Then there is energy storage. Here our focus is on industrial energy storage with wind and solar, where intermittency is a big issue, and how our solutions can kind of help to renormalize that. Then there is a clean hydrogen. So most of the time we don't produce hydrogen, but hydrogen technologies can be co-fitted with carbon capture, which makes them produce loop. And we can actually, we also have solutions to produce green hydrogen, especially in terms of membrane offerings and PSC solutions to produce green hydrogen. And the last but not the least, the carbon capture. So Honeywell has a lot of technologies for carbon capture, especially for natural gas applications.
Many of you might have heard the names Alexol, Cetanol, Cetanol system, which is used for capturing CO2. But this one is slightly different. Here it talks about capturing CO2 from the post-combustion flue gas. This is a low pressure, low concentrated, low concentrated CO2. But there is a separate portfolio which focuses on that because there is someone pointed out earlier, there is a good incentive for CO2 abatement, like there are financial incentives close to $50 per ton. So this technology is also available. So we will cover more today on the renewable fuels. So what are the macro drivers that are driving the renewable fuels? So this chart which on the left you see is the IPCC chart. So basically this chart says that since industrialization we have entered close to 2,000 gigatons of CO2. And especially in the last 20 or 30 years, the rate of CO2 emission is higher. So if you want to stay within the 2-degree limit, we have only a budget space of 1,000 gigatons. And per year, we are emitting close to 50 gigatons of CO2. So that brings us to only 20 years window to want to meet the 1.9 degree scenario temperature rise. And that's why you see that most of the companies, most of the government, everyone is talking about 2050 being at zero, so that 3 million tons per year of CO2 that we are doing today to bring it down. And one of the ways that we can do, there are many ways, obviously, one of the ways is sustainable clean fuels. We can anywhere between 50 to 80% of GHG emissions compared to the standard EVs and law. It also gives additional advantage in terms of reduced particulate emissions, reduced NOx, primarily because the way the chemical composition of this feedstock or products. The second important driver which is driving this green fuels is policy support. So governments over the years have realized that a single flood or a forest fire causes huge economic damage. The cost of that damage runs into millions of dollars. So instead of spending that money to recover that, if we can offer subsidies or viability gap funding or financial incentives or driven through regulations, so we can avoid those incidents. At the same time, we can encourage clean and sustainable fuels. So a lot of policies have come lately. Some of them you can see in Europe, RED, which is a very good directive tool. Carbon standard in the US, and here we have the national biofuel policy. So basically, all of these policies are actually promoting the use of clean and sustainable fuels to help in meeting the greenhouse gas emission targets. The third macro driver is the feedstocks. So we are focusing more on the liquid fuels. So as in terms of technology basically goes through a evolutionary phase. So like for example, if you take an e-forward, which is hydroprocessed ester fatty acid, which is very but mainly it started with the usage of edible oils. Then we moved a little bit to the non-edible fraction. Then we started focusing on carbon intensity of the primary cells, so then getting the algal-based stocks. So there is a technology evolution or the feedstock evolution. Similarly, if you look at the ethanol story, it started with sugar, then we kind of moved to the 1.5% cassava-based feedstocks, and talking about 2G. There is a talking about the mineral versus 2G, and there is a further push to 3G, like capturing CO2 from the flue gas and going into the So technology feedstock, there is an evolutionary trend here. And one of the biggest evolution which is happening is on the lean feedstock, lean organic wet carbon feedstocks, low energy content, available in lot of quantities, and those are the feedstocks which is going to drive this sustainability further. And I think that's going to be the technology trajectory for the next couple of decades. And that's how this evolution is going to be handled. The last one is the financial incentive. So if we just see an illustration, in US, it's a little bit of older slide over 2 years. But the point is, if you take soybean oil, which is like $2 per gallon, and then you kind of produce green diesel. So here you can see the green diesel. But then there are financial incentives based on the green value, plus there is a blenders tax credit. So you are able to make still a lot of money, even after using TikTok and similar case study is shown for used oil. Some states like California and US will further have low carbon fuel strategies and CFS based on the carbon intensity of the feedstock of the use. So you use a feedstock with lowest carbon intensity, get higher credit, so you get the better price. So there are many things. So all these things are driving this particular sector. And so how we respond as a technology company and as an industry is we have three options to produce data. So one is the design standalone greenfield units. Design standalone greenfield unit brings quite a bit of flexibility. We can have a lot of forward-looking feedstocks that can be incorporated in the design phase. We can take we can kind of realize the industry-leading yields, product qualities, and stuff like that. The other option is there are ID assets in the refinery. We can repurpose them to produce the same green fuels. This would be a little bit faster implementation, a little bit lower cost, but it comes with a little bit of flexibility. You cannot design it for every use. The easiest option is to use the existing refinery assets, just co-process, let's say 5%, 8% volume of green feeds to this. So you will actually produce green fuels, least cost of compliance, very easy to implement, and that is one of the multiple ways. So first, let's talk about the green unit, the refinery unit. So this unit is in operation in multiple geographies now. The world's first unit came in the US. There is one unit already in Europe. There is one operated producing green jet fuel in California. Now this technology is so much better because multiple geographies in Australia as well as South Africa. So basically, this technology takes the feedstock like primary sites and converts it into green fuel, basically jet and diesel. It comes in multiple variants. So if you classify it in terms of product, we have a version called green diesel, which totally produces green diesel. Maybe summer diesel plus 3 or minus 3, like a floor point target, and there's a big winter, like minus 8 to minus 10, and then there's a Arctic diesel around minus 20. So that's one variant. We have a jet variant that will produce fully jet, targeting either minus 40, minus 47 jet feedstock. And then there's an intermediate offering where you kind of co-produce some diesel, some jet. So that's another variant. Yet another configuration, this unit is also designed for maximizing green LPG and green naphtha, which can be a steam cracker to produce confidence. The same refining unit can be classified to another variant, which I'll just show it in terms of technically a single stage and a two-stage operation. So in single stage, it's kind of an operation where you have all the three basically systems putting into one reactor and so on. Whereas in the two-stage, you separate the two, get some advantages of doing it in a separate stage, different heat vector, slightly different feedstock flexibility, and then also you can have inlays of co-products of CO2. So this comes in that particular thing. So as I told you, there are a lot of feedstocks which can go into the refining unit, but the key point which I want to make here is if you look at the cash cost of production of feedstock of this product, feedstock plays up very big. For 80-85% of the cost of production is the feeds that we use. So as I told earlier, more the lean carbon and red organic feedstocks that we can pivot, then we can actually significantly reduce the cost, and that actually needs a lot of technology improvement, technology development, and technology. So in terms of catalysts, I think there are three catalyst sections in the first is market. These feedstocks come with quite a bit of multi-entry materials possible to make. So that needs to be used. We need to have a market and have an extended cycle. So that each even a week of shutdown leads to like $3 to $10 million of revenue. So how do you extend the cycle? That's an important particular technology advances. Second thing is the availability of hydrogen. Some locations hydrogen is expensive, some locations hydrogen is cheap. So in terms of deoxidation, there are three competing partners. One is the hydrogen deoxidation, decarboxylation, decarbonation. By having flexibility in the catalyst, we can promote one pathway over the other, and equal catalyst systems which can actually promote one pathway over the other.
So this brings a lot of flexibility depending on the customer need. So drive one pathway which can include, for example, if you take a geo pathway, you use more hydrogen, but then you retain a lot of carbon. In the other way, you use less hydrogen, but then you lose some CO2 from carbon to CO2. So that opportunity is available. But there is identity section which primarily focus on biogenic hydrogen creation. And it is very critical that the active catalyst system is placed here so that you can kind of drive down the FDM and further make sure we can bring more dirtier feeds. There is a goal, the cash cost of production depends on feedstock. So this is particular catalyst system which enables to bring biogenic feedstock. The last one is going to dictate how much of the product slate we are going to get.
Yes, it is basically considering that
the last system is basically going to dictate the catalyst yield, whether it's going to be diesel or it's going to be jet, and that's going to be primarily operated by the balance between some of the systems out there. So this overall catalyst overall, I would say that from a technology perspective, we develop technology. So this technology gives the proven needs, used processing costs, there is a lot of impact on capital costs, but then gives a lot of flexibility in terms of asset gas management is a very important part of this. Right? The last topic that we want to touch for a few minutes is co-processing. So this is the lowest cost of components. I think as a refiner, we need to keep in mind certain criteria when we select co-processing. The first one comes whether we have margins to process biofuel stuff. Is the biofuel stuff degraded or is it going to come contaminated? Whether we have hydrogen availability to convert this biofuel feedstock to fuel. Whether do we have acid gas management capability, because once we process the biofuel stuff, we're going to generate some CO2. What kind of management we're going to have? And then the biofuel feedstocks is going to give a lot of flexibility. What kind of heat management we need to have in place to ensure that there's no proper temperature rise in high. And last but not least, green feedstocks are excellent in terms of biodegradability. But in a hydrotreater, it's going to remain as paraffins. The paraffins are poor for properties. So how much green paraffins we can process without installing additional events, some of the that's going to be important. So obviously everything has a plus and minus, but I would say that this is one way to think about the process. So here I have just kind of given some context as to 5% if you process to the kind of investments you need to do, the kind of technical changes you need to make in the process, and if you go more than 5%, there are going to be cases that this will be right. So that actually kind of dictates how much you can process in the existing. So with that, I'm kind of conclude my talk. Only thing I would like to add is these are technologies which are commercially available, which are deployed. A lot of the refiners are using these kind of products using this technology like refining and co-processing. But in future, there are opportunities for converting feedstocks and efficient, meaning organic feedstocks, and that requires newer technology platforms. And also even in countries like India, where we are focusing more on bioethanol, there are opportunities to convert bioethanol to fuels, not only for blending with gas, but also to convert it to jet fuel and also to blend. So that's a project being very important. With that, we would like to thank the here for making this nice workshop. It's really very event. With a lot of people. Thanks.
Thank you very much, sir, for giving this in-depth detailed presentation on existing and emerging pathways and technology solutions to generate the green fuels, which can lead to a overall sustainability. And basically, now the time is for Q&A, but I would like to mention that we have already shooting the time. So we would like to take only 2 questions with the online speakers only. And the speakers which are here, basically we can discuss on the lunch.
Sir, this is okay. Sir, what is your take on the turquoise hydrogen? We are all talking about blue hydrogen and green hydrogen. So if you can say something about turquoise hydrogen, which is a CO2 cost.
Pramod, is this question for me?
Yes, sir.
I could not hear it fully. Can you repeat what exactly you asked?
Sir, that we are all talking about blue hydrogen and green hydrogen. But there is one term we call turquoise hydrogen also, where it produces hydrogen without any CO2 emission. So what is your view or take on the turquoise hydrogen?
Okay, you mean from methane to make carbon and hydrogen,
Yeah, thanks.
right?
Yes,
Phosphorus.
sir.
Okay. You see, the trouble in that route is that you make a lot of carbon. And unless the carbon is of good quality and better utilization, you will not be able to make a lot of hydrogen in it. You see, now there were talks that it can produce carbon nano onions and carbon nanotubes, and from there you can make graphite grade carbon. But actually, during the process, catalyst is used, and then the catalyst remains inside, and it becomes very difficult to purify those carbon for real high value applications. So I think for green hydrogen, the green solution is the electrolyzer, right? Biomass to hydrogen can play an interim role. It can play a very big role, in fact, till the green hydrogen from electrolyzer becomes cost competitive, which eventually it will become by a lot of capex reduction in electrolyzer. And also we need to have solar power available round the clock at a cheap price. For that you need to have good batteries and good electrolyzer at low cost. So green hydrogen $1 is achievable, I think, in 2050 timeline. Right. But in the meantime, biomass to hydrogen has to play a transition role. And unless you resolve the impurity aspects and make the carbon pure and for better utilization, this route will be facing trouble in terms of it makes less hydrogen and more carbon. So you have to find a good carbon utilization. Yeah.
Thank you, sir. Okay, non-basically, I request Mr. Bhaskar sir to kindly summarize.
So this was a wonderful session because downstream it covered all aspects, right from the essay to refinery and petrochemical integration, various options for the chemicals, sustainable fuels, from green feedstocks, and finally the net zero emissions, the options and solutions. So it is a complete sequence in the session that we covered. So I'm grateful to all speakers as well as audience participating in the good interaction. Thank you very much.
Thank you.
Thank you very much.
Thank you.
Sir. Thank you very much.
Thank you to all the speakers of the session 4. Now, I would like to invite Dr. Manoj Srivastava and Dr. Sunil Kumar to felicitate our speaker, Mr. Pramod Kumar, representing the Momentum. Thank you, sir. Next, I would like to call Mr. Krishnalani to receive a memento as a token of appreciation. Thank you, sir. Now, I would like to call Dr. Balaji Rana to felicitate our chairperson, Dr. Manoj Srivastava and Dr. Sunil Kumar for chairing the session. Thank you, sir. And with this, we end session 4, and I request you all to proceed for tea and coffee in coordinated area near canteen. And we will meet back at 12 for our next session. Thank you.
जान है आधार देश की प्रगति का दुनिया में इतना सम्मान है आगे बढ़ेंगे ऊंचे उड़ेंगे हम सबका यही अभियान है इंडियन ऑयल इंडियन ऑयल इंडियन ऑयल मेरी पहचान है सबके हितों का संरक्षण हो हर कार्य में नव परिवर्तन हो हर दिल में भाव लगाव का हो विश्वास वचन और कर्म न हो आगे बढ़ेंगे ऊंचे उड़ेंगे ये मूल्य मेरा अभिमान है अभियान है मेरी शान है
Bharat Petroleum, a Fortune 500 company, is one of India's leading energy producers and a proud Maharatna company. Our robust network of over 19,000 fuel stations and over 6,600 LPG distributors ensures happy customers pan-India. Our rich portfolio in various sectors like lubes, aviation, gas and international trade puts a seal on our widespread national global reach. For the greater good, we are committed to the environment and society with the motto of energizing lives.
When concepts lead to new innovations, when cutting-edge technology meets world-class project execution, when India's best and brightest engineering minds come together. You create a world-class EPC and total solutions company that catalyzes technology for a sustainable future. Engineers India Limited, an organization that was key to India's energy security, is now South Asia's leading total solutions company, with concept to commissioning services across the hydrocarbons, petrochemicals, fertilizers, non-ferrous metallurgy, and infrastructure sectors. EIL services in these industries and sectors cover the entire spectrum of activities, from concept to commissioning of a project. Our services include feasibility studies, technology selection, design package, feed, front-end engineering design, project management, and EPC services. EIL's state-of-the-art R&D center at Gurugram is pursuing technology development both in-house and in collaboration with premier research institutions and oil and gas companies. EIL is a hub for the country's best technical and professional manpower, trained and empowered with multidisciplinary skills that cover the entire project life cycle. The company is committed to creating value for its clients by pushing the limits of engineering excellence, working on large and complex projects in the most geographically challenging locations worldwide. Engineers India Limited is continuously expanding its international operations with a focus on the regions where it has historically implemented projects: the Middle East, North Africa, and Asia. It is seeking to identify markets where it can provide cost and operational advantages to its clients and distinguish itself from other competitors. One of its recent milestone projects is the Dangote Refinery and Petrochemical Project in Nigeria. With our rich legacy of research and innovation, an impeccable track record of project execution, and a talented and multi-skilled workforce, we seek to be your most trusted business partner. On the back of our unparalleled passion for technology and capabilities, we will continue to provide the highest levels of customer satisfaction through optimal solutions and seek mutual success with our clients. We will exert our utmost effort to fulfill the needs of our valued customers as a world-class, globally competitive, total solutions engineering consultancy and EPC company. India's pride and South Asia's leading engineering consultancy company. Engineers India Limited.
Welcome back. Think about it. An aircraft which runs on the extract of the Jatropha plant. Jatropha oil seed being converted into refined aviation turbine fuel. It's not quite called aviation turbine fuel, but it's essentially green fuel, and it is remarkable that it works. It's there. Yesterday I had a fantastic experience. I was on board a SpiceJet flight, the first flight using a biojet fuel from Dehradun to Delhi. Does this actually work? What does it all mean? I spoke to some of the scientists and some of the engineers and captains of SpiceJet who were behind this. It looks like any other engine of a turboprop aircraft, but that particular engine on the right wing of this Bombardier Q400 aircraft of SpiceJet has 25% of its fuel fueled by Jatropha seed. The rest, 75%, is aviation turbine fuel. What essentially we are talking about is the future of aviation, of efficient aviation, where biojet fuel can have a real mark, a real impact in India. Well, joining us now, Dr. Anjan Ray. Dr. Ray is somebody who's had a huge role in making this entire process actually take place. Thank you, sir, very much for being with us. 25% Jatropha oil in the right engine, 75% aviation turbine fuel. By having biojet fuel, what are you hoping to achieve?
A quick correction first. It's 25% Jatropha oil derived biojet fuel with 75% ATF in the right engine. What we hope to achieve is that we should be able to show by this flight that it is possible to replace both expensive and imported fossil fuel with homegrown fuel. All the carbon that we need for the fuel needs of India can be found within our own borders. And these small steps will add up, just as biodiesel, ethanol, and other initiatives are adding up, to an economy where we will be less and less dependent on the former petroleum economy.
Yeah. And it's much cleaner. That's the bottom line.
It is much cleaner.
Yeah.
The sulfur level in the biojet fuel is less than 10 parts per million, whereas in conventional aviation turbine fuel, the specification is 3,000 parts per million. So we're releasing much less emission into the upper atmosphere. Also, the greenhouse gas emissions, the carbon footprint, is lower by something like 50 to 80% on a 100% substitution basis. We are substituting by 25%, so we'll be saving 12 to 20% of carbon footprint on this flight.
What about the costs?
The costs are a function of the feedstock cost. Right now, this is being produced by farmers in Chhattisgarh at a relatively small scale, and then converted at a very small scale of 4 liters an hour. When you start converting at a refinery scale, if the feedstock is inexpensive enough, it will be competitive.
All right. And what are some of the challenges in getting this technology, this fuel, to other airlines? Is there a lot of interest?
I think there is a lot of interest. We've seen many airlines attempt to get there in the last few years, but SpiceJet has made it. So I believe.
And the Air Force, I believe, has showed some interest also.
The Air Force has shown a lot of interest. The Air Force Chief of Staff has gone on record to say that he would like to fly an AN-32 transport at the coming Republic Day flypast.
Tell us a little bit, one final question, on the chemistry of the fuel. How are you able to blend it with aviation turbine fuel? What is the quality that the Jatropha seed oil needs to actually exhibit?
The Jatropha seed oil needs to be converted to something that looks like, smells like, acts like, and performs like ATF. Literally what we call a drop-in fuel. For this, we remove all the oxygen from the Jatropha seed oil by a process called hydrotreating, and then we rearrange the molecules by a process called isomerization to get the same properties as aviation turbine fuel.
All right, well, Dr. Ray, it sounds tremendously exciting, and let's hope it ultimately works out. For airlines, it'll be a huge, huge saving if the efficiency which you are promising actually works out. 1.8% more efficient than normal engines, right?
Yes, we expect an efficiency of between 1.5% to 2% based on the normal engine performance on a drop-in basis. I would like to credit my team, particularly Dr. Anil Sinha, who led this project, because without getting the quality of product that gives this efficiency, we would not have reached this stage.
And the savings will come through the efficiency because the cost of the fuel itself is still quite expensive, relatively speaking.
Yes, the savings will come not only through the efficiency, but also through lower operating and maintenance costs, possibly less filter changes. And as people start getting sensitive to emissions, if emissions start getting priced tomorrow, then this will win hands down.
Welcome to the latest update program of Drishti IS. In this series, the topic of discussion is indigenous biojet fuel approved for IAF use. An indigenously developed biojet fuel has been formally approved for use on military aircraft of the Indian Air Force, that is IAF. The technology is developed by the Indian Institute of Petroleum, that is CSIR-IIP Dehradun. The provisional clearance or PC certificate was handed over by the Group Director, Center for Military Airworthiness and Certification, that is CAMLAC. Now, information about the fuel. It is prepared from jatropha oil, that is non-edible tree-borne oil. This oil is sourced from Chhattisgarh Biodiesel Development Authority or CBDA. It is procured from various tribal areas of India. Then it is processed at CSIR-IIP Dehradun. Now let's understand the benefits of the fuel. It will enhance the livelihoods of farmers and tribals engaged in producing, collecting and extracting non-edible oils. It will reduce air pollution by virtue of its ultra-low sulfur content. It will contribute to India's net zero greenhouse gas emissions targets. It will enable early commercialization of the technology and its mass production. The aircraft was flight tested and its performance was validated at Chandigarh. Significantly, the technology to produce this fuel was developed by CSIR-IIP in 2013. Dear viewers, watch this topic in Hindi on our Drishti IS Hindi YouTube channel.
Welcome back, everyone. Now we'll proceed to our next session, that is session 5, integrated oil companies. The session will have two invited talks by SEFCO-22 and Dr. David G. Clay. Now, I would like to invite Dr. S.K. and Dr. David Clay to share the session. Dr. Mehdi is Senior Principal Scientist and Head of Distillate and Energy Conversion Division, CSIR-IIP. And Dr. Devendra Singh is Senior Principal Scientist at Automated Fuel and Lubricant Application Division at CSIR-IIP. Over to you, sir.
Hello. Once again, good afternoon, everybody. Now we have talk. One is the keynote talk, and one another is the invited talk. So first talks will be giving. Actually, this is a very important session because in the last 1.5 days we actually saw the presentation which is related to particularly energy. So now actually, and all this technology talked about this downstream processes. Now we have actually opportunity to see and learn that what is the actually how we can get that energy from this from the ground. So we have actually eminent speaker. He is from this ONGC, KB, MIPE, and he is the Chesnis, Visheshan Chesnis, and he is the executive director on ONGC. Now he is actually head of the geological operation and chief the operation geology. He is the currently actually heading the Primary Institute R&D Institute on ONGC. Mostly he actually looking for the exploration and management, particularly different location basin. And Kaveri, he has a lot of experience in the Kaveri, Najaria, and West offshore. So with this few words, I may request Chief Minister kindly present your talk.
all of you, ladies and gentlemen, respected Dr. Ray, sitting in front of my fellow session speakers, my session chair, everyone, a very warm good morning. It was a relative session on Downstream. Unfortunately, I could not attend the last yesterday, but the morning session itself was a pointer to what would have been yesterday's session. Anyways, so from downstream to upstream, here I am talking about hydrocarbon industry in general, and then how hydrocarbon industry would have a role in shaping the energy future for India. When we talk of hydrocarbon industry, it's an industry full of uncertainties, everyone knows. Not how the oil or the beat of elephants in Assam. Probably hydrocarbon industry in India would have kicked off a little later than it actually did. One pilot geoscientist, in defiance of express orders for termination of drilling of a well at a certain depth, not gone offshore, and drilled another 200 meters, we would not have discovered Bombay Island. There were all pressures to terminate that well at L2 and L3 lying just 200 meters below, and rest of the river is. Had it not been on the perseverance and optimism of one Mr. Drake, who was at the stage of bankruptcy, and only the last lender allowed him money worth the last day of operation, we would not have at all found. Hydrocarbon has a long history. It was being used for treating of skin diseases, for lung diseases, for diarrhea. Then it was being sold as a panacea to save the whales, because whale oil was being used for elimination of seeds. It had much less, and people in daily kind of news also, to rid the New York streets of cross-dam, because cross-delivery cars were being passenger transport, and then somebody by the name Rodolph Christian Hans Diesel invented the diesel engine, and the whole scenario of this industry changed. On those notes, let me get into my presentation. I would certainly try to finish it in time. This is all. We will in a very short talk about energy scenario in global and Indian context. We will follow it up with energy future challenges and opportunities. We would also touch upon step taken towards clean energy and net zero, but standing here on the podium as a hydrocarbon explorer, talking about low carbon and net zero, I have to be a little careful. But nevertheless, we'll talk about it. Perspectives of OESC, my organization, will have a little glimpse of it. So this is a very repeated and oft-seen picture taken from the BP Statistical Review of World Energy 2021 and share of market. Yeah. Okay. So world consumption of energy in terms of exajoules, what we see is green is oil, red is gas, gray is coal, coal remains, carbon remains. We have a presence of nuclear energy, but from Chernobyl, from Fukushima, and then the world thinks that it is not an energy which we can really depend as a major supplier and portion in the energy basket. Of course, then there are the renewables, which are from the humble beginnings somewhere in early 2000 to having a broader scope. Of course, everyone knows this dip here is the pandemic related drop, and it is going to remain as a notch for any such presentations which are going to be made years or decades down the line. Well, shares of global primary energy in terms of percentages, presently what we have is 33% oil, 27% coal, natural gas to the extent of 94.2, and of course hydroelectricity, renewables, and nuclear have this have the presence now. Renewables, the graph at the bottom shows a rising trend. Then oil, yes, this dip again due to the pandemic. We have these different sources. Of course, we have spoken about non-renewables, fossil fuels, coal, oil, and natural gas, nuclear energy. I would actually not talk much about it. Renewables are the biomass energy from the plants. Again, it's not a carbon-free energy for sure. Hydropower and ocean energy, geothermal energy, incidentally, ONGC along as said, through its ONGC Energy Center has recently funded and it is still under ready well for geothermal energy, solar and wind energy. We'll talk about it, how we are looking at it. The Indian scenario, key indicators in India, percentages of global average. Now, GDP per capita, we are at about 25%. Energy demand per capita in this was 2000 and today we are about 45%. Energy demand per capita around 35%. This is percentage of global average. Okay. So, coal demand per capita, you can see we are 60%. Major of our power plants are there consuming coal. The energy and economy indicators of India are below the global levels, so they are actually rising. So, a developing country, of course. Primary energy demand for India, as you see, coal still has some prominence in 2020. Total demand is on the right axis here, MMTOE. Now looking at the future, from today to into the future, India's energy demand to become doubled by 2030, 2040 at a strong compounded annual growth rate of 84%. What we had in 2016 and what we are looking forward, we look forward to be at in 2040, the demand would be nearly 2 billion tons of oil equivalent. It's the fastest growing energy consumer and likely to account for 25% of rise in global energy demand by 2040. Not only applicable to the hydrocarbon sector, but also to renewable energy sector in India. Fossil fuels, for the present, we can see the global energy scenario to contribute 75 to 85% of energy mix. Future energy demand of India continuing. What we have is India's production and trade of coal, crude oil, and natural gas in 2000 to 2019. In fact, 20 figures were also there. Not get it here. Yeah, had seen before, production is about 400 for coal, imports 200, making a total of 600. On the oil front, we are mainly dependent on imports. Basically, there is a lot of discussion about how India would be shaping on the availability of domestic oil. Now, there are a few things. One of the most important we see is endowment, and other thing is, optimism in terms of being able to find hydrocarbon in the places which we have not so far been able to, prove. Now, example here is of Vindhyan Basin in Madhya Pradesh, Central India. We have gas over there, a number of wells which are produced tested gas. We have West Bengal Basin, wherein Ashok Nagar has proven presence of hydrocarbon. Only thing is the big elephant is to be seen. It's there, has to be located. Gas as an energy source would be slowly getting over, and import dependence in the gas, because we have KG basin, which is the gas-prone basin, and we have a number of gas fields there. And we look forward that we have more domestic gas production. Vindhyan is coming as a gas-prone basin only, and that's how the picture would be. Structure of energy mix, primary energy flow. So, primary energy demand in India, share of oil and gas would be seen expected to increase to about 38% is what it is. Shaping India's energy future. Here I want to make a few quick references. Basically, it is said that we have exhausted all the oil finds, prone basins, and so on and so forth. But we also have to remember that these are the old basins which get you oil from new areas. And I would refer to soil discovery. Activities were going on since probably 1920s, and after the giants, the ExxonMobil, Chevron, and one different idea, looking at the biogenic accumulation of biogenic gas. EMI success, and today's world is one of the biggest biogenic gas. We talk of, and recently as probably August this year, wherein Neptune Energy has struck hydrocarbon again in an area which has been explored and explored and explored. It's a different idea, looking into the Cretaceous fact. We can talk of total discovery in the Mediterranean, wherein again, after a number of operators, we have biogenic total field impact, that is ENI discovery. Total success has been offshore Namibia. Yes, offshore Namibia, they have such big oil field. Idea is, what I want to say, that it is the new ideas in known areas which can provide new hydrocarbon. Now, of course, we have heard about no carbon and carbon-free and green and all those things, but as because hydrocarbon is going to enjoy a prominent position in the energy basket, 4 at least India. will be worthwhile to keep the optimism alive and get new oil in the old areas. Anyway, getting back to the presentation, it's an oft-repeated statement that India's energy future prosperity will hinge on affordable, clean, and reliable energy source. Scope for further growth in energy demand and infrastructure is huge. India is a large country. India is a development country. India is energy hungry and always has been. The Indian energy sector, electricity sector is on the cusp of solar power and the revolution, and as solar takes over the focus of coals, which is to industry. Again, yes, we would be moving, there used to be a change, there will be a change that has to be managed, then there would have to be adjustment changing for the industry and hydrocarbon industry on the whole. Moving industry and transport pushes carbon dioxide. Now, this is the concern part and a strong air quality. A 50% rise in India's carbon dioxide emissions to 2040 is the largest of any country, even though India's per capita carbon dioxide emissions remain well below the global average. Okay. Now, here again, carbon dioxide remains a concern. However, the carbon dioxide mitigation methodologies we have heard are on, and we are sure that some of these things on a larger scale would definitely offset what is rising. Now again, I talk about my perspective on it because this is what is not good for this. Okay. When you talk of carbon dioxide, CCUS and carbon dioxide, we are taking carbon dioxide, inserting and storing inside subsurface. Now, when we are doing that, I was told in one of such meetings that in Iceland, where this sequestration is happening, they have seen the proof of carbon dioxide being fixed in terms of deposits of calcium and magnesium carbonate downstream where the stream is coming out. Now, my only question to wonder about is that when we say carbon dioxide being fixed as a carbonate, magnesium and calcium carbonate, so from where that magnesium and calcium carbonate coming in there? What we are doing is actually it is some kind of classification, evolution. Are we doing it right? If I look back at hydrocarbon, which was thought of as a panacea for production of shale gas. Now today, hydrocarbon is being opposed by the society all over the place, including for ONGC. We are having difficulty in extracting the hydrocarbon using the technology. There is a lot of social unease, I would say. Okay, a quick perspective on Indian hydrocarbon scenario. We have opportunity in yet to find resources. There is a huge potential about 29.78 BPOE category 1 basis. We need to approach them differently. Category 2 and 3 basis consolidations in opening new area that is happening slowly, and soon we will see some of these coming up. The most prolific basins, of course, everyone knows, I will not read out. These are the proven hydrocarbon basins in the country. We have total open acreage of 350,000 square kilometers, out of which we expect there is total YPF of 20,476 MMT. These are the numbers estimated from the scientific assessments of the basins and the sediment thicknesses and the maturation and so on and so forth. Distributed in 53 places, what we have so far established. So, total yet to find hydrocarbon, YPF for that matter, yet to find the hydrocarbon in emerging place is upwards of 5,000 MMT, 26% of the total. So, the basins which are not yet established hold quite potential, and This is where we as a national oil company are focusing. And we have eyes on millions, we have eyes on third basis. We are looking into decentralized for the presence of refinery and refinery systems which may be of interest. Now, when it comes to the gap in demand and supply, so in order to bridge over the gap, ever increasing gap between the supply and demand of conventional, the need for our to look for the unconventional. What is happening in unconventionals, we have seen in the previous sessions also. China is projected to grow leaps and bounds so far as the total energy consumptions by 2050 years. India is there below it, and then there's a cluster of countries, United States, OECD, Europe, other non-OECD countries of Africa, in the Europe below, have sourced from the International Energy Outlook 2019. During the last 2 decades, exploration efforts were systematically directed towards realizing unconventional hydrocarbon resources of different nations of India. Now, here we are saying unconventional hydrocarbon resources, thereby hydrocarbon hosted in unconventional resources. So we have focused into basement accumulated oil, basins and shale gas. Was targeted. In fact, mother of field in South India, in Tamil Nadu state, is a producer. 2/3 of it produced some product comes from basement hosted oil. We have father field in Gujarat, where again basement is a prolific producer. Well, just a little bit about ONGC. We are an integrated energy company, vertical and lateral. So we have upstream, where in ONGC is there, in price petroleum. Refinery and petchem, we have MRPL, OPAL, OMPL, and EL, and HME. We have our own plant at Zira for the value-added products. 22.5 MMTPA LNC from the Petronet LNC. 726 megawatts of power is expected from the ONGC Tripura Power Corporation. Now, this is being planned to provide electricity to the or augment electricity supply, I would say, augment electricity supply to the northeast. Then there are other companies, these are service, they haven't regional. Well, that statement I must make. When you see a group of companies serve the nation with a broad portfolio of products. So, this is the broad portfolio of products. Again, on the right side, as you see, ONGC, Videsh, MRPL, ONPL, OPAL, and OTPC. And what they do is listed out once again. If I read out, there will be a building, which say that the time, yep, fancy wrapper. Well, ONGC in India discovered 7 out of 8 producing basins. We have been saying that, and there are 2 more likely to be added very soon, the Indian and the. In fact, we list out Indian and the Bengal.
Yes, sorry for this.
Yeah, I know. I read quickly. Yes, again, augmenting the national energy demand through hydrocarbon, we are there in other countries. 15 countries with 35 projects, 40 exploration, 4 development, 14 projects in and 3 pipeline projects. The map is there, the listing of countries is there. Once again, I won't avoid reading this. HPCL we have heard just now from, straight from HPCL. So once again, I'm not going to get into it, but as because we have HPCL now, it's mandatory for me to show this slide. And refinery and petrochemicals, again, on the downstream, our presence, category 1, CPSE, Central Public Sector Enterprise, we have 14 retail outlets commissioned in 21 for the 2 in the current fiscal. That will give us 35 outlets in operation. PS6 facilities and desalination plant commissioned in 21-22. Again, you would have already read it. I would emphasize that we have a strong presence downstream as well. Policy Tripura Power Company Limited again 4,124 million units of power generated, plant availability factor of 65%. So thereby saying that we are there for the clean energy as well, not only hydropower. Shaping the future is our Vision 2040, where we look forward to double the same production, triple the refining capacity, and then GW of megawatts, GW of renewables, and $1 billion for this one new frontier opportunities, which will be coming our way. In fact, our investment in category 2 and 3 basins is over there. India's net zero challenge again, I think this is a slide repeated off screen, but what remains is that carbon dioxide emissions per capita and emission intensity of electricity generation by 2020. So where do we stand? Per capita emissions, the bottom axis, okay, tons of carbon dioxide per capita, we are somewhere around 100 or so. Practicing the emissions policies. Okay, clean energy technology areas critical for reaching net zero emissions, where we have India faces the need to invest in large range of technology, in a range of technologies capable of addressing both existing and new sources of carbon dioxide emissions. Now, industry, rather sector-wise, carbon dioxide emissions, clean energy technology areas, power, industry, transport, and buildings. Okay, so Government of India initiatives towards adopting clean energy, accelerating efforts to move towards a gas-based economy, cleaner use of fossil fuels, particularly in the petroleum and coal. I often repeat these statements, and when I was in college, when I was having a electric motorcycle, it used to give 12 kilometers to a liter of petrol, and today we have a car which gives 30 kilometers to a liter of diesel. So, cleaner use of oil, more efficient use of hydrocarbon. Greater reliance on domestic sources to drive biofuels. Yes, we have already seen that in the first session today. Achieving the renewable target of 450 gigawatts by 2030. This is basically Indian perspective, not essentially ONGC perspective, because I mentioned the figure of 10 in the last slide. In e-mobility and emerging fuels, including hydrogen and digital innovations, we have seen this being discussed in the previous session. I was mentioning about gas hybrid because this is the new initiative, essential initiatives in energy production, and therefore gas hybrid research and technology development contributes to government India's plan to commercialize gas hybrid. So we have in the east coast of India substantial gas hybrid acquisition. It is a technology barrier which has to be broken to get them out of the face to exploit them. Well, the two operational wind power projects, 102 megawatts at Jaisalmer in Rajasthan and 51 megawatts at Bhuj, Gujarat. Total installed capacity of wind power 153 for us. Uranium exploration, okay. uranium exploration MOU has been signed between ONGC Energy Center and Atomic Minerals Directorate for Exploration Research. In my own institute, some work is being done on enrichment of uranium, leaching of uranium. Geothermal energy, I was just mentioned that we have a well going on in Ladakh, Kuga Valley for harnessing the geothermal energy. Soon enough, we want to establish there, but Ladakh area is very limited operational window. Soon in October onwards, the operations will have to stop because of sheer winter there. Solar energy, total solar power of 31 megawatt, another 20 megawatt projects are underway. We see again pursuing research and development of some of the solar thermal energy applications and heat storage materials. Hydrogen generation, again, the ONGC Energy Center, ONGC Energy Center in fact is our flagship for originates and renewables. Development mechanism was PSU 15 registered CDM project with the UNFCCC that yield certified emission reduction approximately 2.1 million yearly. Gas clear reduction has happened. We are using gas for enhancing oil production. Gas clear viewers reducing the gas clearing, and then through various measures gas clearing has been reduced less than 2% of our production. Much more. Carbon capture, utilization, and storage for carbon dioxide sequestration obviously puts focus on reducing carbon emission. Sign an MOU with IOCL for CCSU project development. Basic recovery again, all the gas turbines in Haldia, Uran, Tractor, and HPSC Kakinada has been recovery steam generators. Global Methane Initiative, again, we have a MOU. A voluntary agreement with the USCPA in 2007 for purpose of reducing the methane emission. Digital India campaign functioning in various modes through digitalization, integration, and standardization by harnessing automation. This is our internal Disha process. I think I did this slide again because I have given one warning. I don't want another warning. And therefore, thank you very much.
And information particularly that ONGC CSIR-IIP is irrespective of the energy, geothermal, and gas hybrid, and oil and solar. Thank you very much. Very good afternoon to all of you. It's indeed a pleasure to introduce our next specialist, Dr. David Cleary. And he is heading currently the Center Detroit, which is dedicated developing new technologies to improve transportation. And he started his career from General Motors in 1994. And later on in 2013, he joined Karan. He received his PhD in mechanical engineering from Ministry of Wisconsin. And we are now eagerly waiting to hear your views about the sustainable transportation. And since the whole sector, the transportation sector, is trying to take a paradigm shift towards electrification. And in the midst of this, so there is a degree, we hope that this talk may enlighten us to take a conscious decision towards sustainable transportation. Over to you, David. Thank you very much.
Thank you very much for the introduction. I want to begin by thanking Dr. Ray and all of the IIP team for inviting me. I have to say this has been my first trip to India. And the hospitality has been amazing. Thank you very much. And I just only wonder why I waited so long. So thank you. So energy is incredibly important. Environment is very important. I'm going to talk about both. I'm going to talk a little bit about transportation. Why transportation? Because after crude oil today, and what happened about crude oil goes to the transportation field. So transportation is incredibly important for all of us as a society, but also for oil and gas as part of the We talk about holistic. When I talk about holistic, what this means is energy production, energy transformation, or making fuel, or making electrons, and of course, energy consumption. Yeah, very effective goals, net zero. I would say net zero. That means we need to work in all the phases. Also, when I say holistic, I'm talking about life cycle emissions. We're not addressing life cycle emissions, we will not solve our climate challenge. Okay? So, very important life cycle emissions. So, I know everyone here knows Saudi Aramco very well, but I'll just be very brief and have a very short introduction. So, we're going into chemicals enterprise, where we go from energy production, transformation, as well as energy consumption. We manage and have the privilege, in fact, of managing the world's largest oil reserves in the world. We produce a lot of oil to the world every day. In fact, the number is 7.2 barrels a day is low today. Significant natural gas is about 70,000 employees globally. So global research centers, of course. And all of our activities and all of our centers in Saudi Arabia. But the global research centers here work on recovery, discovery, production. They work on materials, refining, and transportation. The ones shown here in color are specifically focused on transportation. I'm specifically into the trade research center. So what are we doing in transportation? What we're doing reducing emissions. There's a tremendous need to reduce CO2. We talked about CO2 yesterday being 23% of the global CO2 production. That's correct. If you look at greenhouse gas, which includes methane and fuel, and we look at energy and non-energy related greenhouse gas, we're talking more like 50%, but still a significant number. We collaborate and we commercialize, so we're focused on having impact, and of course, technology development. That's where it all begins. So I'll talk a little bit about our dual challenge. We've seen this throughout the last decade. Very important to meet the world's energy needs. Okay. And when I say meet the energy needs, I mean reliable and affordable. If it's not affordable, it's not available. Okay. And as you just saw, energy demand going up, populations are going up. We're targeting 40% larger population, 40% more by 2100. And 2100 seems like a long time from now, it's not very long. So all those people need energy. The other goal for us, of course, is net zero greenhouse gas emissions. So how do we get to net zero? Certainly it's a challenge. It's a better challenge for us. But we have efficiency and speed. Efficiency is very nice because it's cost effective. It reduces CO2 and also the benefits for the consumer of energy. Right? So efficiency, we heard the first day the importance of all machines having efficiency, and we need is carbon capture, a lot of carbon capture sequestration. Electrification, every time I hear electrification, it's electrification of the powertrain of the engine. It's very important. But pure electric batteries are part of the solution, but we need to think about where that energy comes from. We need to think about where those batteries are made. When we talk about hydrogen at the bottom, we need to think about where those electrolytes were made. Okay? If they're made in environments that have high carbon footprint, then the result material won't be low. Synthetic fuels I talked about a little bit, and of course biofuels we know is part of the solution. So talking a little bit more about energy, but we all know energy is important, but why? We're all engineers and scientists, so how do we quantify it? So I plotted here a very important metric like Human Development Index versus total energy demand per capita throughout the world, right? And you see a very nice trend of, higher Human Development Index means people consuming more energy per capita. This measure is really quality of life, but it's also a very important parameter here is growth national index. How much are we as individuals able to contribute to society? Okay, this is a very important metric. So it basically means you need more energy to have better quality of life and to contribute more as individuals. Energy is obviously very important to us per capita, and the per capita is increasing, and not surprising to see these charts a minute ago. This is global energy demand. The green is the OECD part of the world. The blue are the growing parts, the non-OECD parts of the world. Not surprising, energy is going up very rapidly, so this is energy demand. here, how are we making that energy? As we just saw, petroleum, natural gas, coal, of course, nuclear, other renewables. But if you look at the green line there, then even the renewables are not offsetting demand increase. So that's a very important statement, right? So we're not needing demand increase in the world with our renewables. Okay. Renewables are part of the solution, but they're not the only solution. Energy transportation, again, we're over half the petroleum goals. Transportation, the car park's increasing from 1.3, just like the car park, to 22 billion vehicles in the world. So a lot of transportation, what are we going to use? This is the chart from EIA. Says we use diesel, gasoline, and heavy fuel oil, and jet fuel, and so forth. So there's a lot of fuel going against us. So how do we deal with reducing greenhouse gas emissions? This is another chart shows where we're at. So if you look closely and this before 2020, we look like we're flattening out. This is energy related CO2 emissions. Okay, it's not total greenhouse gas, but includes land. This is energy related. It looks like we're flattening out, but we're back in the rise, and the current trend is to keep increasing. That's clearly not so what do we have to do? We see the policy says we're going to keep producing the same amount of CO2 every year. That's not true. So we need efficiency in all areas. We need renewables and waste, need electrification, needing carbon capture sequestration. If you look in the middle, it's maybe hard to see, but in the middle, there's some green areas. There's wind and solar. They're part of the solution, but they're contributing. They're not going to solve the problem for us. Okay. This is how we see it. So, if we look at passenger cars, efficiency support, hybridization support, it has to be affordable. If it's not affordable, it's not available. Okay. So we are working on low-cost hybridization solutions. Better electric vehicle fuel cells. Again, where's the energy? Where's the hydrogen coming? What's the carbon footprint? Okay. Renewable fuels, we worked on a lot of renewable fuels. We have 2 pilot plants, one in Europe, one in Saudi Arabia that we're working on. Taking renewables, but we have excess renewables making fuels. Heavy duty commercial is very similar, except we take all carbon capture, natural gas, aviation offsetting, direct air capture. This is, so I remember, very capable, of course, in terms of process engineering. So how do we make process efficient and we need innovation? And we're in fact working on low carbon capture. We're looking at ammonia as well as low carbon fuel, as well as natural gas. So I want to say a little bit more about life cycle, and I think everyone here is quite familiar with this concept. But we need to think about mining materials. How much energy does that take? Where's that energy coming from? What's the carbon footprint? Processing materials, assembling parts, making parts, refrigerating parts and assembling parts, and then giving it to the end user and then recycling them. It's incredibly important. We have to look at all aspects of the carbon footprint. So we see that a vehicle, or let's say our goods footprint here, and then there's an energy, what we call all wells to the planet. So this is basically how much energy is required to produce energy, and then how much is required to transform energy to fuel electricity. So then this is the chart. I'm not going to get into. Every detail here, but the first bar is a very basic internal combustion engine, so the carbon footprint is high. So we have hybridization, is the third bar here, much lower. We have what we call gasoline compression emission. This fits well in a lot of applications, a little bit larger, like truck application, so much lower again. We can look at hydrogen from blue hydrogen, not zero, depending on how we generate the hydrogen. We can look at hydrogen from fuel cells as well, which is not zero, depending on the fuel cells, how we generate the hydrogen. The balance here on the right in the US, then the US is not zero, of course, and on the right is today's China. Now, where's it being up? But today, you look at that chart and say there's a lot of internal combustion engine technology. Hybridization is relatively low cost. We can have impact today. We can push it across, many markets in the world, and we can reduce carbon. And this is a study from Corporate National Lab, and it looked at two scenarios. One scenario is let's improve efficiency of the internal combustion engine. The second one is let's push EVs, 50% EVs in the market. And in fact, for the US market, it shows that either choice is a good choice, meaning where you reduce carbon footprint, but it's not dramatically different. Okay, either EVs or internal combustion engine. And same results for China as well. And it's related to the energy or carbon footprint associated with the grid. So a little bit of thinking about India, and this is today's situation, and this is the baby we wrote, so we'd love to have a discussion with the team here. So let's look at one vehicle, the individual vehicle, we'll look at some others in just a minute. The carbon footprint of electrification is shown in the bars, and the gasoline engine is blue, and diesel engine is green. And it shows they put charging this in the day, in the summertime, we have a lot of demand for electricity here, of course, with air conditioning in India. Then in fact it needs price target. That's today's rate, right? It's included in the bottom renewable stuff that's today. Higher than gasoline, certainly higher than diesel. And if we look at the charge in summer and winter, it's a little bit lower, so it's more renewable available. And then if we charge it overnight, of course, it's less renewable, so it's going to go up the total carbon density of the total battery vehicle. So these are all things we need to think about on a life cycle basis. And this is an analysis my colleague did, and again, this is today's grid. But if you look at all of India, the blue data is basically an internal combustion and gasoline car today. And it shows all of India for one car, it would be 13% better greenhouse gas emissions compared to electric vehicles using gasoline. But in other vehicles, it gets 0%. So it depends on the application, depends on the grid, of course. The diesel engine, some applications that's solar, some don't. Depending on the region, the northeastern region, very good grid, very good renewable opportunity, very good opportunity to have better electric vehicles with low carbon, but not many vehicles. I think it's about 2% of vehicles in the region. In the eastern region and western region, those numbers are all negative. The new better electric vehicles today have a higher carbon footprint. Of course, renewables are coming, the grid is getting clean throughout the world. Of course, internal combustion engine. So this is a changing situation. So a little bit on what we're doing international. The two engines here, so we are building engines, we're designing new engines, we are driving efficiency to reduce CO2 emissions. The two engines on the left is spark ignition engines, we're looking at about 10-12% reduction in CO2. That's also translates to 10-12% better fuel consumption. So this is relative to that and turbocharged engine. Very important solution. We have designed and demonstrated in vehicle engine controls aftertreatment system that gets it 90% below the Euro 6E. That's on road molecules in Europe, and that's the -7 road drive emissions. So the toughest emissions we can do, we're at 90% lower than Euro 6E in India. And that is market is very important. On the right is the TCI, the gasoline combustion ignition engine. This is more for larger SUVs like trucks, but we are targeting 35% CO2 reduction. So this is 35% fuel improvement, fuel consumption improvement. So good for the customer, good for the environment. It's something that does not cost very much today. It's something that we can implement compared to alternatives. Okay. Just briefly and community. Just briefly, these are some of the work we've done in the so we worked on a lot to meet California 2027 standards. Everything is incredibly efficient, but there's more room to improve. So this is an example of 10% lower CO2, that's 10% fuel savings as well. 90+% NOx emission reduction. The second category is the more conventional engine design, something that we can implement relatively soon. It's about 8% CO2 reduction, and again, 90% lower NOx in critical area to work in. The third one I threw up is this is the DOE, US DOE. So I remember those engines in 2014, same engines were about 42-44% breakdown efficiency, and they're getting 55%. So that's literally 3 right, I'll continue the normal carbon capture. Our goal is 50% reduction. And just to expand on that, for conventional diesel engine, we can run naphtha on it. We run a huge range of fuels in environmental. Naphtha is a nice fuel, especially it has higher CP and carbonation because usually the low heat value is a little bit higher and the HTC ratio is a little bit higher than diesel. We pick up about 5% more CO2 on these applications that are very efficient today. So everything kind of helps as well. And we've also run gasoline. This is gasoline in the diesel engine. So this is developed with a lot of hardware development and control development. But you can see smoke compared to diesel, like 85 to 90% lower budget consumption. So all of these fuels in diesel are very possible, I will, once we develop a better system. The next step, of course, for us is moving to hydrogen. I'll say a word about mobile carbon capture. So this is more of an exploratory activity in transportation, but it's a real activity, of course, we're going to cover today. Carbon capture capacity part of this mission, we started with just F-250 in the lab when we used a solid solvent and got about 10% reduction. We moved very quickly to the further product. We got about 8 times smaller, plus about 25% CO2 reduction. And now we get up integrated into plastic carbon, which is generating an amazing amount of CO2 emissions. Right now, we are emitting about 40% lower CO2 emissions. So, and the system on the right looks small if you're used to refining. It looks big if you're used to transportation. So we're working on new technology to make this even smaller. And I think you've seen this enough, but I am so impressed with some chemical engineers. I'm a mechanical engineer by training. Chemical engineers can make it absolutely amazing. I just saw it at the facility here making good from plastic. So this is truly impressive. So of course we can start with renewables. We can use CNF forming carbon capture, sequestration, and hydrogen. We are getting boost with ammonia for fertilizer today, which is ammonia for power generation as well. And recently, of course, we can make methanol, we can make gasoline, kerosene, and future growth, we can make diesel, all from captured carbon point source, which we have activities in air capture, and of course, hydrogen production is very important. So, yeah, this is I would say, very active program. We are working hydrogen in terms of combustion engine, so why not hydrogen fuel? So what we do is quite expensive. Right? It's quite a big one. So this is a chart plumbing. And this is hydrogen fuel cell, and this is battery like in here. So expensive. This is hydrogen combustion engine, natural gas, and diesel. So much more reasonable cost. In addition, once you think about transporting hydrogen in the field, we don't really want to deal with the 100% purity hydrogen part. So thermal combustion engine solve that problem. In addition, if we look at the work done by Oregon up here, it says the peak efficiency for fuel cells is pretty low levels, and commercial vehicles are pretty high levels. Okay, so that thermal combustion engine can be quite efficient. So we are working. We have many customer activities today focused on developing the next generation hydrogen thermal combustion engine. And this is just a kind of a landscape where fuel consumption versus low. And we're working in an upgrade and kind of maximize thermal efficiency and maximize torque. So I hope that was interesting and useful. I just want to say very briefly, and that doesn't take time. So we have a cool challenge. We have to provide affordable, reliable energy. So I'm going to say reliable. Request it's always available, but we don't have it for day. So reliable means constantly. So we need to reduce greenhouse gases. And we're going to need a number of things to do that. So we need efficiency. We should not stop working in efficiency. There's a lot of engines that are going to be produced still today. Maybe they're electrified, but there's going to be a lot of power anymore. Renewables for sure. Working on it, but it's not the only solution. Carbon capture has to be part of the solution. And it needs to be working. Biofuel electrification, nuclear synthetic using hydrogen, all clean. If you take a holistic approach, from energy production, transformation, to consumption, it's key, but life cycle emissions. We have regulations that say you got to let the make zero emissions. No, that's not true. And if we continue with this perspective, we will not solve the challenge. It's very important to solve. I would say there's been a important opportunity in price efficiency and pollution, 90% plus low pollution. That's great. There's some very tough regulations today. We need short-term solutions. We can't wait until 2050, 2060 or further. Many things can't continue to today. We need to implement the program what you like. Longer term, we're looking at innovation and hydrogen. So with that, I very appreciate it.
Thank you very much, Dr. David. The session is open for the discussion. No questions, sir.
Thank you very much. So, Dr. David, we covered the holistic approach to look at how to implement sustainable transportation. Basically, related three important things that we need to make all this more efficient to reduce emissions and how to have a net zero emissions from that. And even we have gone to the extent that how to CO2 emissions and emitting, how to capture it. So, extremely, it's really an enlightening kind of option. Thank you very much. Over to you. Similarly, I also plan to position it actually we have to do overview, particularly in the futuristic Indian context, source of the natural gas and API, which is very important for the energy source. Not only that, we also summarize that what actually ONGC working and the hydrocarbon sources. It touches upon every possibility like gas hydride and solar energy, wind energy, geothermal energy, and even hydrogen generation also. And we learn a lot of the share from you. We also once again thank you.
Thank you to all the session speakers. Now, I would like to invite Dr. S.K. Mehti and Dr. Devendra Singh to felicitate our speaker, Shri S.N. Fitness Ji, by presenting the memento. Thank you, sir. Next, I would like to call David G. Kelly to receive a memento as a token of appreciation. Thank you, sir. Now, I would like to call Dr. Atul Ranjan to felicitate our chairperson, Dr. S.K. Mehti and Dr. Devendra Singh for chairing the session. Thank you, sir. Now, the time has come to draw a curtain to our program and proceed towards our delivery session. Looking forward, I heartily invite Dr. S.K. Mehti to deliver a special talk on circular regulation in marine fuel and possible solution in the Indian countries. Dr. Mehti is Senior Principal Scientist and Head of Discrete and Heavy Conversion Division at CSIR-IIP. He joined CSIR-IIP in 2012 and till now he contributed a lot in research and development activities in downstream refinery. I am happily invite you, sir.
Thank you and good afternoon. It is of course a large talk. I am reviewing your minds and we also, of course, it is a overview of the marine fuel. Now we all talked about last 1.5 days about the energy scenario in India and global. So we mainly cover up in the energy scenario, particularly transportation fuel, in the land transportation fuel. But I in this actual talk, I will discuss that what is the criteria of specification or regulation, particularly going to be concerned about the marine fuel. So what is actually marine fuel and we particularly known as the Marco 2020 or IMO 2020. Before 2020, there is there is no regulation particularly concerned about this sulfur specification in the marine fuel. Even in India also almost around 3 to 4% sulfur is used as marine fuel. But from the 1st January 2020, there is a drastic change. You can see the change of the sulfur specification, particularly come down from the 3.5% and to the 0.5%. This is the second time drastic change of the marine fuel. So there is a lot of stringent also specification also in marine fuel, which is the previously is the untouched, particularly before 2020. So this actually change affect also Indian refinery and how it's actually cope up with this drastic reduction of the sulfur. We'll just see that how actually Indian refinery cope up with this drastic sulfur reduction. So what is the way actually, how actually Indian refinery and global refinery produce the marine fuel? So if you see particularly marketable product for the refinery is mainly the gasoline, jet fuel and diesel. And after that, whatever the basic product left after that we can sell out at the marketed and the refinery particularly with the as the name of the fuel oil. And this fuel oil particularly can generate actually maximum generation happen in the distillate unit. Also, this is the bottom part of the SDHC and also natural gas. So, what are the use of this fuel oil, particularly where they use it? So, mainly there is the two options the use of the fuel oil. As you know that those refineries produce lot of energy, but its production need also a lot of energy. So internally, actually, refinery also most of the that fuel oil, whatever generate refinery, they also use actually their internal purpose. Mostly that is the high sulfur fuel oil. And there is the after 2020 and bunker fuel, which is also known as the low sulfur fuel oil. They also use some alternatives. So how actually price of this low sulfur fuel oil if we compare with the crude oil? If you see that the crude oil and the crude oil in the middle of this and the fuel oil comes below that the crude oil, which means whatever the crude refinery getting, the fuel oil they are selling in the lower price. That's why that the fuel oil market for the refinery is not attractive. Attractive is that they can produce the gas oil and the diesel, that is the more profitable for the refinery. So how actually, where actually India stands for the production of the high sulfur fuel oil and low sulfur fuel oil, whether we produce enough fuel oil, low sulfur fuel oil, which can cope up our demand supply gap. If we see that particularly top of the line, actually that is the total production of the high sulfur fuel oil, the top portion. It is around 10 million metric tons per annum. But our consumption, as a total, our consumption is around that 6 million metric tons. That means we have 3 million metric tons of the surplus of the fuel oil. But unfortunately, that all the surplus maximum amount of surplus fuel oil, actually high sulfur fuel oil. So let's see that where actually we need that low sulfur fuel oil requirement. If we see that India produces low sulfur fuel oil around 0.5 million metric tons, but our requirement is the low sulfur fuel oil is the 1 metric ton. So we produce 0.5 million metric ton of low sulfur fuel oil, which is required for the marine fuel, but in the base we want to produce the up amount, that is the 0.5 million metric ton. So this gap of the 0.5 million metric ton, how actually fill up this gap? Get the several will fill up the gap. One is the process of the low sulfur fuel oil. Another is the process of the more crude oil, whether it is possible or not. If we convert high sulfur fuel oil to the low sulfur fuel oil, and last but not least, with our what are the alternative, we can find out the fuel oil. So let's look at this Indian scenario where we stand. If we see here, particularly top of this gap, it is around 90 million metric tons actually to get high sulfur fuel oil. And out of these, and if we see that those sulfur fuel oil, those sulfur crude, actually we are getting around 60 million metric tons. So around actually if we convert the percentage of the high sulfur crude actually Indian oil, Indian refinery process, it is around 70 to 75%. That means most of the refinery, Indian refinery actually process high sulfur crude oil. So one Indian refinery process high sulfur crude oil, that is the profit margin. If we see right hand side the profit margin, if we process high sulfur crude oil and price difference of the low sulfur crude oil, it is around $15 per barrel. That's why to get more margin, Indian refinery process the high sulfur crude oil, and of course Indian refinery have that infrastructure to process the low high sulfur crude oil. So therefore, low sulfur process of the crude oil is also not at the option for the Indian refinery. So there is another option that process the more food. If we process the more food, there is the possibility to get the low sulfur fuel. So whether it is possible or not, this curve also shows. The below graph is shows that installed capacity in Indian refinery, and top of this line shows the processing capacity. That means Indian refinery at present actually over capacity, process the over capacity around the 5 to 10%. So there is a no gap or buffer zone to process more crude oil, and at this moment, particularly without any expansion of the refinery. So it means also that with this actually there is no possibility to actually produce the low sulfur crude oil, which is required for the marine fuel. So what is the other option? Option is that the conventional desulfurization process. So if we have high sulfur fuel oil, if we remove that high sulfur crude oil to low sulfur fuel oil, that can be used. The problem is that the high sulfur fuel oil is the highly contaminated feed. So if we catalytic process and distillate reactors, use the catalyst poison very fast. Catalyst reactivate very fast. So with this reactor system, this kind of actually high sulfur fuel oil we cannot process. But there is also other option, that is regulated rate reactors. Unfortunately, those regulated rate reactors all over the world is very popular reactor classification, but unfortunately still today there is no regulated rate reactor hydrogeators in India. But we are getting in very near future, particularly in this HPCL Hyder and Humanivar University, Humanivar Refinery, and in ISL also most of that is planning to adopt that regulated rate reactors, reactor system which can actually convert to high sulfur fuel oil to low sulfur fuel oil. Of course, there is another option also, we are also working, that is the hydrotherapy. This is the upcoming technology. So this is the legal scenario, how actually we can do the high sulfur fuel oil to low sulfur fuel oil. So if we summarize here, before the 2020, we actually produce a lot of high sulfur crude oil, which is actually non-compliant crude oil that is shown in the left-hand side. So what actually do it when they use actually high sulfur fuel oil? They have actually caustic starving system built up in the sea or bunker. They whatever the sulfur dioxide or the SOx produce that is actually stopped by the caustic soda. But where actually there is the limitation, where is the sulfur percentage actually go very high, that kind of stable system also not work. So what are the compliant fuel which is actually presented in the right-hand side? Low sulfur fuel oil, as I told you, particularly in the Indian scenario, we cannot produce the low sulfur fuel oil, and even if we produce also low sulfur fuel oil, particularly high sulfur fuel oil to the low sulfur fuel oil, there is a high cost also to convert that. So we have very good opportunity. As you know that we talked about that Indian actually diesel economy. We have just produced a lot of diesel, and that can diesel can be used as a very fuel. So there is a lot of scope. The most suitable option, particularly in Indian context, but obviously if we compare the price with this high sulfur fuel oil, with this marine diesel or marine gas oil, there is a huge price difference that is around approximately 10.5 rupees per liter. So that also we are in this signal owner. So let's see, let's check whether we have actually sufficient diesel and we can that diesel can be used as a low sulfur fuel oil, particularly the marine purpose. Top of the line actually we show that the India produced that diesel, high-speed diesel. What is the amount of this thing? Around it is the 110 million metric ton of the diesel we produce in India. So what is the consumption of that? It is around the 80 million metric ton. That means around 30 to 40 million metric tons we have actually sufficient amount. That part of the sufficient amount of the excess surplus diesel can be used as a low sulfur fuel oil in the marine fuel. So that's why it is the only option, particularly at this moment, that whatever diesel is produced, that can be some part of this can be used as a marine fuel. So what are the alternatives we have? So we talked about this biofuel, particularly as you know, other transportation fuel, particularly land transportation fuel using the biofuel. And we also heard about this LNG, and it is also touched about the methanol, hydrogen, and that can be also obviously better that can also use as a marine fuel. So if you concerned about the marine bio oil and marine fuel, let's see that the hydrogenated vegetable oil, which is known as HVO, particularly this kind of the vegetable oil used in the Norway, but particularly short distance ferry service in the Norway. But obviously, there is a one negative point in the cost. Cost of this kind of the vegetable oil, of course, they need actually hydrogen, particularly for the hydrogen, and that's why the cost actually went up. And of course, there is of course limited source capacity also there. There is also possibility. We also talked about the LNG that can be also used. But the bio-LNG, that's the only problem is the high NOx emission. That also be taken care of. Obviously, in Indian context, we can see that methanol is a very high possibility. But particularly, my context is that the doubtful is the sustainable. If we see that particularly producing the ethanol from the sugar cane, 1 liter ethanol are actually required at 300 liters of the water. So in India also we have the very Indian future, we have also very participation of this particularly water. If we calculate, if we see the energy, particularly biofuel and food oil, 1 gram of the crude oil provides us around 32 to megajoule of the energy. And of course, it also be around 0.2 gram per chemical. But in the same time, we put the 1 gram of the coal, we put calculate the energy density, it is only 6 megajoule, and but it can be actually 0.8 gram of the chemical. So, convert to this bio to the chemical other than the fuel, it is the best option, it is the economically best suited option. So, in this context of the LNG also has that also the executive director of the ONGC that we have also very bright future of the LNG. But if you see the 2020 energy scenario, that all total energy budget in India is around LNG power around 6.5%. But with the 2030, we have really more than covered, it is around 15% of the total energy budget. So there is a big possibility that LNG can be used as a very influence. So let's take that energy scenario also. If we see that total oil and LNG capacity, it is around 188 billion cubic meter is available. So that can be used as a source of the marine fuel. It is as you know, at this moment, 50% of the LNG actually we are imported. So there is the facility and the whole box facility CPR, we have also facilities that storage facility particularly. If you see that all these they have Hajira and Kochi, fine Kochi, that we have actually capacity to storage the gas component. So whatever LNG we import, that infrastructure already we have, and that infrastructure can be used as a source, and that facility can be used as a very clear and very well, particularly in the concept of the LNG. So advantage of the LNG, as you can see, this is actually available most of the countries, and it is the good network as I started the import and export also. It is also comparable, the cost is the comparable to the low sulfur fuel oil, low emission of the carbon dioxide. Even this LNG can be used also as internal combustion engine and also as a fuel engine. Of course, this advantage is also there. If we see that low density and we require large scale. So, we import LNG, obviously natural gas, we have to liquefy, and that liquefaction needs lot of energy. We call the cryogenic storage tank, and that cryogenic storage tank, of course, very energy intensive. And also there is a leakage of this methane, because if they methane at the very high rates of the greenhouse gas emission. That is the disadvantage. But in India also, we see that the Kochi refinery already started some work to use that LNG as a marine fuel. So we are also in the progress the use of the LNG, how to use the LNG in the future. Then how do we take a look at the methanol? We are also talked about the methanol. So where we are taking this stand, we see that there is a lot of sources of the methanol, particularly methanol can be produced from the coal and natural gas, obviously natural gas, liquidity, solid oils, and carbon dioxide, particularly now there is a lot of talk about the carbon dioxide converted to nickel. Even IIT also working on this area, even biomass. Particularly two sources is most important in the coal and natural gas. At this moment, almost 90% of the methanol is imported. So it is around 1.8 million metric tons at the methanol is imported. This is around 90%. And of course, there is a future, particularly we see actually in India at this moment, produce around only very, very small, around 0.2 million metric tons of the methanol from the natural gas. But as I mentioned that India do not produce methanol, maximum methanol is imported from the outside. Because of the importing of the outside methanol is much cheaper than the produce of this methanol here itself. Because we do not have lot of natural gas. But we have actually very abundant amount of the coal. If tomorrow coal gets fired and then converted to the methanol, that is actually good opportunity of this methanol production. In this area also our sister labs in number actually they are also putting actually demo unit production of the methanol, particularly coal. So tomorrow we will get success, we can actually produce methanol from the coal itself. So if you see actually price lot of this methanol compared to the petrol and ethanol. So let's check the production of the cost 1 liter of the petrol is around for the refinery. Of course, it's a very dynamic every day, every time actually we need that price will change. So it approximately 30 rupees actually production cost of the petrol, whereas ethanol is actually 46 rupees. So it is higher than the petrol cost. But in the methanol cost, particularly in India, of course, this is a very optimistic cost. It is around 20 rupees per liter. But government pay particularly for this, actually, still government pay actually petrol it is the same as the production cost. It is the methanol, they actually give some amount to the company. Activity stand for the 38 rupees in the methanol and ethanol will around stand for the 68. But when it goes to the customer, that is the price with the tax. If you see the petrol price at this moment, of course, it is the more than 95 value actually taken from the 2021. It is more than approximately petrol price is the 95. Now, where is ethanol stand? It is around 70. Of course, if you see that price paid by the government and the price with the taxes, only 2.8% of the GST actually imposed in the ethanol to promote more ethanol production to the company. So that's why the price is still at a low compared to the petrol. But if you see the petrol price 36 to 95, 59 rupees actually government deduct from this actually net result tax. Whereas ethanol is the same because we do not produce at this moment ethanol, so therefore tax return is still with the trend. So my emphasis is that in near future there is a scope to use the ethanol as a futuristic for the marine. So what is the advantage? I told that advantage is a lot. Ethanol is the more pure. Obviously, as compared with the between the liquid and the liquid purchase, they are both the less expensive storage capacity. They are less expensive. Obviously, there is also disadvantage. Still, that ethanol is the much density, the much lower than the fuel oil. That's why it is required 2.5 times larger than requirement. Obviously, as you know, as I explained that the methanol also produced from the natural gas from carbon dioxide, which actually simultaneously produce lot of carbon dioxide. So that carbon dioxide capture is very much required if we need to actually zero net carbon. But look at this advantage, we are also Kochi Refinery particularly, they have also started the 3 boats and 7 cargo almost ready to run by this ethanol. So what are the other options? Of course, this is the task by everybody. Of course, this is a very fascinating, I can say that the hydrogen, there is a lot of root of the hydrogen, gray hydrogen, blue hydrogen, green hydrogen. I do not touch, but I only want to emphasize that tomorrow, obviously, for the decarbonization, hydrogen only one route which can be actually replaced by the carbon. But we have to implement particularly very effectively to actually mitigate that carbon emission. Obviously, when we go to the gray hydrogen to green hydrogen and substantially price is high, particularly at this moment, but in near future, maybe 2050, green hydrogen has probably Dr. Das mentioned it can be come down at the $1 per kilo. Of course, we will look after that. So what is the advantage? Obviously, there is a lot of advantages that it is a very best option, particularly when you talked about the decarbonization and I think it is the best option. It can be used at the ICE, not only that ICE can be also used at the fuel. Key challenges, obviously, there is key challenges, hydrogen, we use hydrogen, again, the low density fuel, it need actually compress, particularly compress at basically 50 to 70 watts, and oil compress so high pressure, it is very dangerous. So safety is one concern. And as we know that the hydrogen is a very small molecule, so if you liquefy also, there is a very intensive process to liquefy the hydrogen. So that is the challenge. Obviously, at this moment, the very costly already I done. If you look at the today oil market, today oil market is around 120 billion actually dollars, but we are expecting that 2020 it actually increase the inventory with a huge sum, particularly in the term will be 8 years. So obviously there is a future in the hydrogen, not only in the transportation fuel, of course in the marine fuel, land transportation, hydrogen is very important. So obviously this is the last, not the least battery. Obviously we are also working all over the world is the working and one thing of the battery. We are very industry for the battery. Obviously, when we talked about battery, it is a very obviously battery only disadvantage is that with a huge space required, and not only that, is the oil very heavy. This is the key challenges when you use the battery, particularly for the marine fuel, because this needs actually huge amount of the battery. Obviously, and the land itself at this moment we do not have actually charging facility. So when we talked about the PTR or in the Banka fuel, there is also need actually charging facility. And that charging facility, you can imagine how actually it will be done. And what is the time frame of this charging facility? So this kind of actually advancement, actually research R&D is required, of course, to reduce the charging facility also. Obviously, this is the cost effective, this is a very highly cost. And uncertainty, particularly when we talk about the battery, that battery can use, battery system can be used in the coastal area, not in the district. Because when battery is charged, then there is no option to charge it. So that kind of actually thinking battery can be used, that's why it can be dual mode, obviously. Dual mode, it can be also used the deep mode and DID, but it is only on single mode, there is also uncertainty there. So these are the things, and if we see today actually, where actually all over the global where they stand, the number of things in the operational or in the order, in the very near future will be operated. Particularly that with the LNG and battery aggregation, methanol, particularly the battery 170, the passenger ferry it is already operational, and in LNG 56. Passenger ferry it is only operational. In methanol, can also see that the methanol it is 11 and because as you know that we are also importing from the outside the methanol. That methanol thing can be done also by itself with this slight modification of that engine. So that's why there is also very high scope of the methanol. So actually readiness of this technology, we see that the high sulfur fuel particularly left hand side because it is already operational and the left hand side actually will projected in the near future that is the renewable sources, hydrogen, electricity. So green actually shows that the readiness and going to stay the green the red colors actually that shows that still we have to do lot of work. So if we see that comparing the high sulfur heavy fuel oil compared to the hydrogen and only electrical facility, then we have actually lot of work to do actually good implements. Here also in the LNG as emission and compared to LNG, ethanol and LPG also compared to the renewable is the middle point. That is almost very middle. So that is all from my side. Thank you very much for your comments.
Thank you so much, sir, for such a stimulating talk and for being a part of this event. I highly appreciate your gracious presence. Now, I would like to invite Dr. Kritika Kauli to felicitate Dr. Nike. Thank you, ma'am. Now, for the lecture session, I would like to invite Dr. Ashish Kumar, event scientific coordinator, for announcing the poster awards and certificate distribution.
First, I would like to thank our poster examiners evaluating large number of posters. So we were having around 75 posters, and it was really challenging to select the best three as all were technically rich and well presented. So we have two best posters in each category. And so let me start with the third one, the third prize. So here we have Mr. Andre Wamba from CSIR-IIP. I'd like to invite our senator, please come on the stage and give the award to all the winners. Next, the prize goes to Mavi Surana from IOCM New Delhi. So Mayor Sarma is also there. Second prize goes to Swagat Kumar Nayak, NIT Roundtable. The second prize goes to Dr. Fausto Gray, IIT Kharagpur. Not here. Okay, so now let me set the first prize. The first prize goes to Niranjani Soman from CSIR-IIP. So we have one first prize winner, Saurabh Vasis from CSIR-IIP. Thank you so much. And I request participants can collect their certificate from registration desk.
And congratulations to all the awardees. Now, I hand over the stage to Dr. Kritika Kohli, our Team Scientific Coordinator.
Thank you so much. You all are waiting for lunch, so I will take that this time. But I'll summarize the event and then give my closing words. So it's been a pleasure to have you all with us today after having scientific discussion for 1.5 days for this event. We are now coming towards the closing of the event, and this our national symposium, Shaping the Energy Future, Challenges and Opportunities. We started in 2017, and now we are in the 6th of the series. And this is mainly organized by our research scholars, trainings, project staff of CSIR-IIP with the coordination of the young scientists. This year's SEFCO theme was Innovative Steps Towards Clean Energy for Net Zero India by 2070. And the theme was related to India's conjoint strategy to better climate change, which included committing to reduce its carbon intensity by 45% cut total carbon emissions by 1 billion tons by 2030 and pledging to turn net zero India by 2070. With these words, I would like to provide a brief summary of the event. The event started with a brief about the symposium by Ms. Swati, research scholar, CSIR-IIP, followed by welcome address by the director, Dr. Anjan Gray, and inaugural note by Ms. Shukla Mistry, Director of Refinery, Indian Oil Corporation Limited. In her welcome address, Ms. Mistry expressed the need for regulational changes in the energy sector to meet the goals as per the Paris Agreement. Citing the International Energy Agency, she said that by 2050, there is a need to convert the emissions from the use of fossil fuels to net zero. She also discussed the expected use of green hydrogen in carbon capture and storage. Then there was a magnificent talk by our chief guest, Mr. Prabdas, Managing Director, Chief Executive Officer, HPCL Nuclear Energy Limited. He emphasized on making carbon capture economically viable. He concluded the talk by saying, whenever India wants, India has and can deliver. So it's in our hands to deliver now. Thanks to our guest of honor and chief guest for enlightening us. Later on, the symposium presented an exclusive spectrum of scientific discussion from our invited guests from different industries, academia, scientists, and technologists. More than 200 delegates from various organizations have registered for this symposium. Apart from the scientific session, we had social presentation also, and for which there were more than 70 participants. After this forum, we had 3 technical sessions on day 1 on the different sustainable themes, and on day 2, we had 2 technical sessions related to downstream, refinery, and perspectives of Indian integrated oil companies. For all sessions, we had in total 7 keynote speakers and 11 invited lectures from different academic institutions and oil and gas industries. And it covers a huge various topics related, starting from smart integrated renewable energy systems to lithium-ion batteries, the capacitors, and role of unconventional energy resources toward net zero targets, hydrogen generation from electrolytic wastewater treatment. And today, the event covered downstream industries, including petrochemicals and the integration of biofeedstock in the current refinery. We had wonderful talks and possibly our young researchers and scientists and participants incorporate their innovative ideas to achieve India's net zero goal early 2027. That's our baby. In the valedictory session, we had a special talk from Dr. Samir MIT, Senior Principal Scientist, CSIR-IIP. Thanks to all our distinguished speakers. And I would like to congratulate all the organizers for successfully conducting this event. Thanks to all. And after this, I would like to give a closing note for the event. Our distinguished guests, our participants, I would like to thank all on behalf of the organizers and the participants of the event. It is indeed my pleasure to make a few closing remarks and express gratitude to all those who made this event a reality. Thanks to our chief guests and guests of honor for taking their time, precious time, and enlightening us through their views and thoughts. A special thanks to our director, Dr. Anjan Bray, for giving our research scholars and young scientists an opportunity to organize the national symposium like SEFCO and providing constant support throughout the event. Thanks to SNGPC and KDMIP OEDC for being with us today. A special thanks to our international delegates, Dr. David Cleary and his team from our American Center, United States. Thanks to our invited speakers who joined us online as well as physically for taking out their precious time from their busy schedules. We greatly appreciate our sponsors for their support for conducting this event. Thanks to all. I would like to thank our media person for his special coverage of the event. Not with the least, special thanks to our event organizers, our research scholars, our young scientists, and other administrative staff of CSIR-IIP for passionately participating in this event and making it a successful one. Thank you all for being here today. And there is one announcement: all the distinguished guests, delegates, please drop your ID cards at the registration desk for the recycling. Thanks. And now I would like to call all the organizer members of the event. Research scholars will receive an appreciation award from our director, Dr. Anjan Bray. Please come on the stage, all organizers.
और बैठा दो
को बैठा था फिर बहुत मैं तो पीछे से दिखेंगे नहीं वो चाहे कहते हैं उनको इधर उधर पीछे वाले 2-3 जने तो भाई वाला भी खड़ा है बराबर
Convener with Mr. Vedant Joshi and Mr. Vijay Patel. Congratulations to all organizers for successfully conducting this event. All objects in the safe way. Please join us for lunch in the voting playground. Thank you.
you.